Beneath Jupiter's thick swirling clouds lies a world full of wonders and mysteries. For centuries, telescopes showed us only its mesmerizing storms and striped atmosphere. But NASA's modern probes have now pierced that veil, revealing a realm of crushing pressures, alien chemistry, and unimaginable forces. From the famous Great Red Spot, a massive storm that has raged for centuries, to its deep metallic hydrogen core, Jupiter hides secrets that challenge what we know about physics, chemistry, and astronomy. Before we begin the video, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below, and settle in for a fascinating journey to uncover what lies beneath the clouds of Jupiter. Jupiter is truly a giant among planets. If you could somehow scoop up Earths and drop them inside, it would take almost 1,300 of our worlds to fill this massive ball of gas. And deep inside its heart, the heat is unimaginable. The temperature at the core can soar to about 43,000 degrees Fahrenheit. But here's the thing, you can't land on Jupiter. There is no solid ground waiting for you down there, because it is a gas giant. Instead, you would be diving into a thick, swirling atmosphere. If you looked around as you descended, you'd see an endless parade of clouds, shades of brown, yellow, red, and white, sweeping past in broad bands. These clouds are what give Jupiter its iconic striped look. The deeper you go, the more extreme things get. The atmosphere, made mostly of hydrogen and helium, is squeezed so hard by the planet's immense pressure that it actually turns into liquid. Far below, at the very centre, lies Jupiter's mysterious core. No one knows for sure what it is, perhaps a molten, slushy mass, or maybe a rock so heavy that it is 14 to 18 times the mass of Earth. Then there's the planet's most famous feature, the Great Red Spot. This colossal storm has been raging for centuries in Jupiter's southern hemisphere. Its upper layers tower more than 5 miles above the surrounding clouds, and the storm itself is about 1.3 times wider than Earth. When NASA's Juno spacecraft visited in the year 2017, it revealed that the storm reaches at least 200 miles down into the atmosphere, 30 to 100 times deeper than the deepest oceans on Earth. And that might not even be the full depth. The Great Red Spot is colder than the rest of Jupiter's atmosphere, where the upper cloud layers can drop to a frigid minus 234 degrees Fahrenheit. Yet strangely, right above this storm, scientists have recorded the highest temperatures ever found on the planet, around 2,400 degrees Fahrenheit, which is even hotter than molten lava on Earth. Experts think the storm's fierce turbulence might be creating gravitational and sound waves that heat the air above it. Oddly enough, the bottom of the storm is warmer than its top. Humans have been watching this massive, swirling vortex for more than 150 years. At one time, astronomers thought it was dying, slowly shrinking and losing strength. But to their surprise, data from the Hubble Space Telescope showed the opposite. The winds around the outer edge have been speeding up by about 1.5 miles per hour each Earth year. It may sound tiny, but it matters. The winds at the edges already roar at nearly 400 miles per hour, far faster than the fiercest tornadoes back home. Yet if you were somehow floating in the centre of the Great Red Spot, you might not feel much. The winds there are much slower. No one is certain what powers this relentless storm. On Earth, storms lose strength when they pass over land. But Jupiter has no land at all, so nothing is slowing it down. Its atmosphere is in constant motion. Hot gas is rising, cool gas is sinking, twisting and mixing. Just like storms on Earth, only on a far grander scale. Many astronomers believe the Great Red Spot may have begun when several huge storms merged into one. Now, it keeps itself alive by pulling in cool gas from below, hot gas from above, and even swallowing smaller storms that wander too close. Unfortunately, Jupiter's thick cloud cover hides the storm's roots, so no one can see what lies far below. Some wonder if there's a volcano under there, but that seems unlikely. Jupiter's gaseous makeup means it has no crust for magma to burst through. The storm's striking colours, ranging from pale salmon to deep brick red, are another puzzle. One theory says there might be a layer of colourless gas far below that reacts with sunlight's ultraviolet rays, creating the red hues. But no one knows for sure. Your guess is as good as mine. And Jupiter is not the only planet with a monstrous storm. Over on Saturn, there's the so-called Great White Spot. This storm appears about once every 30 years. It starts as a bright patch in the clouds, but then stretches and stretches until it circles the entire planet. Scientists believe it is actually a massive system of thunderstorms, with lightning flashing more than 10 times a second at its peak. The biggest mystery about the Great White Spot is where it gets its power. Some think the sun provides the energy, while others say there must be a hidden heat source deep inside Saturn that keeps it going. The Great White Spot, also called the Great White Oval, is one of Saturn's most breathtaking and mysterious weather events. The name comes from its similarity to Jupiter's famous Great Red Spot. But while Jupiter's storm has been raging for centuries, Saturn's storms come and go, arriving in enormous bursts of fury every few decades. These colossal tempests are so large and bright that they can be spotted from Earth with an ordinary telescope, standing out against the golden hues of Saturn's clouds as vast patches of white. Some of them stretch across several thousand kilometers, big enough to swallow our entire planet several times over. In the years 2010 to 2011, the Cassini spacecraft, which had been orbiting Saturn since 2004, had a front-row seat to one of these legendary outbursts. This particular storm was also known by two other names, the Northern Electrostatic Disturbance, because it created intense bursts of radio and plasma interference, and the Great Springtime Storm because it erupted as Saturn's northern hemisphere was moving into spring. Cassini's instruments made astonishing discoveries. The white clouds showed a sudden drop in acetylene, a rise in phosphine, and a strange, unexpected drop in temperature right at the storm's core. Even after the storm's visible clouds faded away in the year 2012, Saturn wasn't finished. Two enormous hot spots in the atmosphere merged and released a giant belch of heat and ethylene into space, a dramatic aftershock to an already mighty event. These storms are not random. They seem to appear in a kind of rhythm, roughly every 28.5 years, when Saturn's northern hemisphere tilts most toward the Sun. Usually they occur when the planet's position in its orbit corresponds to a solar longitude between 90 and 180 degrees. But the 2010 storm broke the pattern, erupting unusually early, just after Saturn's equinox. Astronomers have officially recorded 6 great white spots. Medium-sized storms, called synoptic scale storms, sometimes appear in between these great events and may be related. For example, in 1994, a storm observed both from the ground and by the Hubble Space Telescope appeared in Saturn's northern hemisphere and may have been connected to the 1990 Great White Spot. Before 2010, many storms formed in a region of the southern hemisphere nicknamed Storm Alley, around 36 degrees south. Between 2002 and 2010, several of these storms flared up. The first appeared in early 2004, the second in late 2004, nicknamed the Dragon Storm, and the third in early 2006, which was observed by astronomers Eric Bondu and Jean-Luc Dauvergne. These storms lasted for months at a time. Another long-lasting storm began in late 2007 and rumbled on through the first half of 2008. By 2009, the southern storm alley was so active that storms seemed to erupt almost continuously, right up until the 2010 Great White Spot exploded, but this time in the northern hemisphere. During the Voyager 2 spacecraft's flyby in 1981, scientists saw a northern version of Storm Alley, located between 33 and 38 degrees north, right where the 1903 and 2010 Great White Spots later appeared. Curiously, no southern Great White Spot has ever been seen. This might be because Saturn's southern hemisphere is harder to observe from Earth. But that's about to change. Between the years 2025 and 2038, the southern hemisphere will be tilted toward Earth, giving astronomers their best chance yet to spot one. If such a storm behaves like its northern cousins, the next southern Great White Spot might appear after May 12, 2032, when Saturn's south pole points most toward the Sun. The first known Great White Spot of the telescope era appeared in 1876, and it was spectacular, visible even with very small telescopes with lenses only 60 millimeters wide. Why none were recorded before then is a mystery, much like the puzzling century-long gap in observations of Jupiter's Great Red Spot in the 17 and 1800s. The storms usually start as small bright patches but quickly grow, stretching across the planet. The great white spots of 1933 and 1990 both expanded so much that they wrapped completely around Saturn. They form a head that swells in just a few days to more than 10,000 kilometers wide, kicking up a turbulent wake that circles the planet. The great storms of 1990 and 2010 rose 40 to 50 kilometers above the surrounding clouds and shone more brightly than the rest of Saturn's atmosphere. This brightness suggests that the storm clouds were coated in freshly churned water ice. Early in the 1990s, computer models suggested that these storms are triggered by thermal instability, a kind of atmospheric tipping point. But in 2015, two planetary scientists from Caltech proposed a deeper explanation. As Saturn's upper atmosphere cools with the seasons, heavy water rains out first, making the upper layers lighter. Then, as cooling continues, the remaining hydrogen and helium become denser again. When this heavy layer breaks through to the layers below, the instability sparks a giant thunderstorm. The delay between the coldest season and the storm explains why they don't happen immediately after winter. Jupiter, they say, doesn't get storms like this because it has far less water vapour in its upper atmosphere. The head of the 2010 Great White Spot was made of about 55% ammonia, 22% water ice, and 23% ammonium hydrosulfide. The water ice was brought up from about 200 kilometers deep in Saturn's atmosphere by powerful convective updrafts. This storm also produced an unusually high amount of lightning, about 10 bursts per second, compared to just a few bursts per second in smaller Saturnian storms. Saturn's spectacular rings block our view of the planet's northern hemisphere from Earth during its winter solstice, so historical records have gaps. But Cassini, which arrived shortly after Saturn's winter solstice in 2004, gave scientists the first chance to watch these storms unfold in detail, revealing a drama that is part science, part celestial art, and part pure chaos. Let's take a trip to the far reaches of the solar system and visit Pluto, the largest known dwarf planet we've discovered so far. This icy world is small, lonely, and distant, yet its atmosphere is surprisingly impressive. It stretches far above Pluto's frozen surface, forming more than 20 delicate layers stacked like a giant invisible cake. Each layer is unimaginably cold and tightly packed, holding on to precious bits of gas in the darkness of space. By the way, our own moon also has something that scientists call an atmosphere, though in its case it's so thin that it's barely there at all. This ghostly shell of gas, known as an exosphere, contains helium, neon, and argon. But here's the wild part. It is about 10 trillion times less dense than Earth's atmosphere. That's so thin it's almost nothing, like a whisper compared to a hurricane. While sailing through the vastness of space, you should always keep an eye out for black holes. These cosmic monsters are regions where gravity becomes so powerful that nothing, not even light itself, can escape. Imagine a trap so perfect that even beams of light, the fastest things in the universe, are caught forever. But black holes are not always quiet and hidden. Sometimes they erupt like a galactic volcano. When they do, they don't spit out molten rock, but instead unleash enormous blasts of pure energy. These outbursts can rip great cavities into the surrounding clouds of gas and dust, leaving gaping holes in space itself. Not long ago, astronomers spotted one of the largest cosmic craters ever recorded. Using powerful radio and X-ray telescopes, they discovered a supermassive black hole that had thrown a cosmic tantrum eons ago. This violent event took place in a galaxy cluster roughly 390 million light-years away from Earth. The crater left behind by this ancient outburst is so enormous that you could fit 15 entire Milky Way galaxies inside it. Try wrapping your mind around that. It's like fitting 15 oceans into a single drop of water. As you continue your imaginary voyage through space, be careful where you land. Some worlds look harmless from afar but hide terrifying secrets. Take K2141b, for example, a planet that orbits a star outside our solar system. At first glance, it might seem a little like Earth. It has vast oceans, clouds, and even rain. But there's a shocking twist. These oceans are made not of water, but of molten rock. The surface of K2141b is a blazing hellscape, covered in seas of lava that plunge dozens of miles deep. In the daylight, temperatures soar to around 5,000 degrees, hot enough for the molten rock itself to boil away into the atmosphere. Then, violent supersonic winds, racing at nearly 1 mile per second, sweep this vaporized rock across the planet to its cooler, night side. There, the fiery vapor chills, turns back into liquid, and falls from the sky as rain. But instead of water droplets, it's raining molten stone. On Jupiter, the Great Red Spot is a gigantic storm swirling in the planet's southern hemisphere. The upper edges of this storm tower more than 5 miles above the surrounding clouds, and the whole thing is almost 3 times wider than our Earth. In the year 2017, NASA's Juno spacecraft gathered detailed data about it. Scientists discovered that this colossal vortex stretches more than 200 miles down into Jupiter's atmosphere. That's between 30 and 100 times deeper than the deepest oceans on Earth. And those are just the conservative estimates. The true roots of the storm may plunge even further. The Great Red Spot is colder than the rest of Jupiter's atmosphere. In the upper cloud layers, temperatures drop to a bone-chilling minus 234 degrees Fahrenheit. But closer to the core, the planet heats up dramatically. The highest temperatures ever recorded on Jupiter were found directly above the Great Red Spot, where the heat can soar to a staggering 2,400 degrees Fahrenheit, hotter than molten lava on Earth. This intense heat may be caused by the storm's own violent movements, which create powerful gravitational and sound waves that heat the atmosphere. Interestingly, the base of the storm is warmer than its top. If you stood in the storm's calm center, you might not feel much wind at all. But at the edges, the winds rage at speeds of 300 to 420 miles per hour, faster than even Earth's strongest tornadoes. For comparison, here on Earth, a wind of just 60 miles per hour is strong enough to lift a person weighing about 170 pounds off the ground. At 75 miles per hour, trees can be ripped from the earth, roofs can be peeled away, and mobile homes can be flipped over. At 150 miles per hour, even cars can be sent tumbling through the air. Imagine then the unimaginable destruction the Great Red Spot could unleash if it ever appeared on our planet. Thankfully, that could never happen. Earth simply doesn't have the special conditions needed for such a storm to form. Studying the Great Red Spot has never been easy for scientists. One of the main challenges is Jupiter itself, a world more than 1,000 times larger than Earth and over 300 times more massive. As a gas giant, Jupiter is made mostly of hydrogen and helium. Beneath its thick clouds, there's an immense ocean of liquid hydrogen swirling around the planet's core. And since there's no solid ground, there's nothing to slow the storm down. This is why the Great Red Spot has been spinning without rest for centuries. On Jupiter, hot gases rise, cooler gases sink, and the two mix together to create massive circulating storms, similar to how storms form on Earth, but on a far grander scale. Astronomers believe the Great Red Spot began when several enormous storms merged into one colossal cyclone. Since then, it has kept itself alive by pulling in cooler gases from below and hotter gases from above, while also absorbing smaller storms that cross its path. Each time it swallows another vortex, it grows even stronger. Still, there's much we cannot see. Jupiter's thick clouds hide the planet's lower atmosphere from view, leaving astronomers to speculate about what lies beneath. Could it be a huge volcano? Probably not. Jupiter's gaseous nature means it doesn't have a crust to crack open and spew molten material. And then there's the mystery of its colour. The Great Red Spot's shades shift over time, from whitish or pale salmon to bright orange and deep brick red. One leading theory suggests that far below the visible storm lies a layer of ammonium hydrosulfide. This substance may react with cosmic rays or ultraviolet light from the sun, creating the storm's striking red hue. But for now, it remains only a theory, adding one more mystery to the many swirling inside the most famous storm in our solar system. Astronomers have been keeping their eyes on Jupiter's Great Red Spot for almost 2 centuries, with continuous observations dating back to the early 1830s. But the story of this colossal storm reaches even further into the past. The very first record of it goes all the way back to the year 1665, when it was described as a permanent spot swirling in the planet's atmosphere. This means the storm has been raging for nearly 400 years, far longer than any storm on Earth could ever survive. However, this legendary tempest is changing before our very eyes. Since the dawn of the 21st century, it has been shrinking. In the year 2019, astronomers noticed something strange. The storm's edges began to peel away, with smaller fragments breaking off like shreds of paper and then fading into nothingness. If this trend continues, experts believe that by the year 2040, the Great Red Spot might lose its iconic oval shape and become perfectly round, or it might vanish entirely. Oddly enough, as it is getting smaller, it is also reaching higher into Jupiter's atmosphere and taking on a richer, more intense orange colour. The exact cause is still a mystery, but scientists suspect it could be the result of a chemical reaction happening when fresh material from the deeper layers of Jupiter's atmosphere rises to the surface. Of course, the Great Red Spot might be the most famous storm in our entire solar system, but it is far from the only one. Jupiter itself hosts other enormous whirlwinds, including a smaller but still fierce anticyclone nicknamed the Little Red Spot, spinning away in the planet's vast and stormy skies. Recently, astronomers noticed something astonishing. The winds swirling inside Jupiter's Little Red Spot had grown wilder, reaching speeds of nearly 400 miles per hour. That's faster than a commercial jet and strong enough to tear apart anything in its path. But over on Saturn, there's a storm so enormous and strange that it makes even Jupiter's tempest seem modest. This colossal tempest is called the Great White Spot, and it is unlike anything else in our solar system. At first, it appears as a bright patch in Saturn's thick atmosphere, but it doesn't stay small for long. Within weeks, it stretches and spreads, wrapping itself like a glowing white ribbon all the way around the planet, a sight so vast you could fit our entire Earth inside it. This cosmic spectacle doesn't happen often. In fact, it appears roughly once every 30 years, when Saturn's northern hemisphere leans toward the Sun. Scientists believe that the changing seasons on Saturn trigger this monster storm into life. But here's the twist. What begins as a single spot quickly transforms into a gigantic system of thunderstorms, the kind so fierce that lightning flashes more than 10 times every single second. Imagine an entire world wrapped in continuous flashing light, as if the planet itself were caught in a never-ending strobe. The greatest puzzle, however, lies in what fuels it. Some scientists suggest that sunlight alone powers the storm's violent winds. Others disagree, pointing to patterns in the clouds that hint at a hidden source. A deep internal heat rising from Saturn's core, feeding the Great White Spot like a secret furnace buried far below the clouds. In the distant icy reaches of our solar system, far beyond Jupiter and Saturn, lies the windy and mysterious world of Neptune. Among its strangest wonders are enormous shadowy tempests called Great Dark Spots, swirling storms that rival Jupiter's famous Great Red Spot, yet are far more fleeting. The most famous of these storms, GDS 89, short for Great Dark Spot 1989, was first seen in the year 1989 by NASA's Voyager 2 spacecraft during its historic flyby of Neptune. This was the first time humanity had ever laid eyes on such a feature on this distant planet. Like Jupiter's Great Red Spot, Neptune's Great Dark Spots are anticyclonic storms, meaning the winds swirl in the opposite direction to smaller cyclones. But they are different in important ways. Inside them, there are surprisingly few clouds, and instead of lasting for centuries like Jupiter's Great Red Spot, these Neptunian storms are short-lived, usually appearing and fading away over just a few years. Based on Voyager 2's observations and later studies using the Hubble Space Telescope, Neptune seems to spend a little more than half of its time hosting one of these massive dark tempests. The Great Dark Spot of 1989 appeared in Neptune's southern hemisphere. It was dark and shaped like an elongated oval, stretching roughly 13,000 kilometers long and 6,600 kilometers wide, almost exactly the size of Earth. In appearance, it closely resembled Jupiter's Great Red Spot, but unlike Jupiter's storm, it had the ability to drift north and south over time. Around its edges, Voyager 2 measured winds roaring at up to 2,100 kilometers per hour, or about 1,300 miles per hour, the fastest winds ever recorded anywhere in the solar system. Many scientists believe the Great Dark Spot is actually a gap in Neptune's upper methane cloud layer, revealing darker layers beneath. Over time, its size and shape were seen to change dramatically. The storm also created brilliant bright white clouds just above the tropopause layer, similar in appearance to Earth's thin, high-altitude cirrus clouds. But while cirrus clouds here are made of tiny ice crystals of water, Neptunes are made of frozen methane crystals. They floated between 50 and 100 kilometers above the main cloud deck, and unlike Earth's cirrus clouds, which fade within hours, these Neptunian clouds lingered for 36 hours, the length of 2 full rotations of Neptune. Dark spots like this one tend to form in Neptune's troposphere, lower than the brighter upper clouds, and they can last for months at a time. But when the Hubble Space Telescope tried to photograph the Great Dark Spot again in November 1994, it had completely vanished. Astronomers suspect it was either covered by new clouds or had dissipated entirely. Interestingly, smaller companion clouds that had formed with it remained for some time, hinting that a cyclone might survive even after the dark appearance disappears. These storms often fade away if they drift too close to Neptune's equator, where the planet's Coriolis forces, which help keep them spinning, weaken. Voyager 2 also spotted another smaller storm in 1989 called Dark Spot 2, which had completely faded before 1994. Since then, the Hubble telescope has been our only tool for spotting these features, as it can see Neptune in the blue light where they stand out. In 1994, a new storm, the Northern Great Dark Spot, formed in the Northern Hemisphere but disappeared sometime between 1998 and 2000. Another Northern Dark Spot appeared in 1996 and lasted until before 1998. In 2015, Hubble detected a Southern Dark Spot, which drifted toward the pole before fading in 2017. Then, in 2016, an almost identical storm to the original Great Dark Spot appeared in the Northern Hemisphere. This new Northern Great Dark Spot lingered for several years, though it's unclear if it still exists today, because our view of Neptune is limited. In 2018, astronomers spotted a new dark storm in Neptune's northern hemisphere, the first one Hubble had ever observed from its birth. This storm was smaller than Voyager 2's original Great Dark Spot, yet still massive, about 7,400 kilometers wide, larger than the entire Atlantic Ocean. In August 2020, it unexpectedly stopped drifting toward the equator and reversed direction, baffling scientists. Around the same time, a smaller storm nicknamed Dark Spot Jr. appeared nearby, measuring about 6,300 kilometers across, before eventually fading away. Some scientists believe the appearance of Dark Spot Jr. might have been linked to the reversal of the larger storm's motion. Studies of these storms, including the Southern Dark Spot and the Northern Great Dark Spot of 2018, suggest that they are often preceded by 2 to 3 years of increased cloud activity in the region. Their disappearance, on the other hand, may be caused when bright companion clouds drift into their centres, blocking them from view in blue light. Looking ahead, astronomers are eager to return to Neptune for a closer look. In 2021, NASA considered sending a spacecraft called Trident to visit Neptune and its large moon Triton, but chose instead to send 2 missions to Venus. Another concept, the Neptune Odyssey, is a proposed flagship mission that could launch in the year 2033, with the goal of orbiting Neptune, studying its atmosphere, and exploring Triton in detail. Even China's space agency has published plans for a nuclear-electric mission to this icy giant. Neptune's great dark spots may be short-lived, but they remain among the most spectacular and mysterious storms in the solar system. Fierce, fast, and ever-changing, swirling in the cold blue depths of a world more than 4 billion kilometers from the warmth of our sun. Neptune hides some of the most mysterious tempests ever seen, the Great Dark Spots. These are not just patches of shadow, they are gigantic storms born in regions where the planet's air pressure is unusually high. That's the opposite of what happens here on Earth, where storms usually appear when the pressure drops. At the very edges of these swirling monsters, the winds can scream at speeds of up to 1,300 miles per hour, fast enough to circle the entire Earth in less than a day. So far, astronomers have counted 6 such dark spots on Neptune. They seem to rise from deep within the planet's atmosphere, and the rule is simple. The darker the storm, the brighter the surrounding clouds of frozen methane appear. But Neptune is not the only planet with a taste for wild weather. Over on Saturn, another monster rages, a storm that, at first glance, looks surprisingly like a hurricane or typhoon on Earth. It even has a central eye and bands of clouds spiralling around it, yet any Earth storm would seem like a mere breeze in comparison. On Saturn, the eye alone can be as wide as 1,250 miles, enough to swallow several countries whole. Around the edges, bright clouds race along at 330 miles per hour. And then comes the strangest part. This storm is shaped not like a circle, but like a perfect hexagon, a six-sided weather pattern. When astronomers first saw pictures of it, they had to check twice. It looked too much like storms back home, but it was far, far larger. The hexagon's eye is nearly 20 times bigger than any hurricane eye ever recorded on Earth, and its winds blow about 4 times faster. Even more puzzling is that Saturn's atmosphere contains very little water vapour, the stuff that helps feed Earth's storms, yet the hexagon has somehow survived for decades. Stranger still, it is locked in place at the planet's north pole, unmoving, as if pinned to the spot by some invisible force. Beyond the gas giants, scientists have been finding other strange worlds, known as super-Earths. These are planets heavier than Earth, but lighter than the icy behemoths Uranus and Neptune. Some are made entirely of rock, others of gas, and some are a blend of both. They can be as small as twice the size of Earth, or as huge as 10 times our planet's mass. Sadly for explorers, they are all far beyond our reach for now. Out there are also countless mini-Neptunes, worlds that could be gas dwarfs, ice giants, or massive rocky planets, none of which exist in our own system. What does set our solar system apart is its king, Jupiter. This enormous giant is the largest and heaviest body orbiting the Sun, aside from the Sun itself. It wields such intense gravity that it can shape the entire system's destiny, and sometimes it even eats planets. Roughly 4.5 billion years ago, when Jupiter was still young, a massive protoplanet, about 10 times heavier than Earth and made of rock and ice, slammed into it. The force of the impact shattered Jupiter's core, mixing its hydrogen and helium with heavier materials. Over time, those heavier materials sank back toward the centre, forming the dense core we see today. If Jupiter swallowed a planet once, it may have done so again, and might do so in the future. Scientists suspect that in the early days of the solar system, there were far more large planets than the few we have now. For instance, the region near Mercury is empty today, yet around many other stars such zones are packed with planets between the size of Earth and Neptune. In those chaotic early years, young stars were surrounded by swirling disks of dust and gas. From that debris, planets began to grow, like seedlings sprouting from soil. Small rocky planets formed close to the star's heat, while gas giants took shape farther out, where it was cold enough to keep hold of lighter gases. Back then, the planets' orbits were anything but neat. Some were long and stretched, swinging dangerously close to the Sun before drifting far away again, pushed and pulled by the gravity of other worlds. One idea, called the Grand Tack Theory, paints Jupiter as the great disruptor. In the first few million years, it may have moved inward toward the Sun, like a ship tacking toward a buoy before drifting back outward. On its way, Jupiter may have swept up huge clouds of debris, colliding with forming planets and altering their paths. Once Saturn appeared, the chaos eased somewhat, but the damage, or reshaping, had already been done. Jupiter may even be partly responsible for Earth's oceans. It can capture and redirect asteroids, sometimes flinging them into interstellar space, and sometimes sending them crashing toward the inner planets. 66 million years ago, a space rock struck Earth near what is now the Yucatan Peninsula in Mexico, triggering earthquakes, volcanic eruptions, towering tsunamis, and a mass extinction, including the end of the dinosaurs. Where did that rock come from? No one is certain. It might have been an asteroid or perhaps a comet from the distant Oort cloud at the solar system's edge, nudged from its path by Jupiter's immense gravity. In this way, the early solar system was like a giant cosmic pinball machine, with Jupiter acting as the flipper, batting comets and asteroids toward the Sun. Some broke apart under the Sun's tidal forces, scattering fragments across space. Ironically, it was in the aftermath of that catastrophic collision that our mammalian ancestors began to thrive, meaning that without Jupiter's meddling, neither Earth as we know it, nor we ourselves might exist at all. Jupiter's role in shaping the solar system was not gentle. It shattered ancient planets, cleared the way for smaller worlds like ours, and may have both destroyed and delivered the ingredients for life. It is a planet of contradictions, destroyer and protector, predator and guardian, and the solar system still dances to the rhythm of its gravitational pull. Jupiter might be the very reason we cannot seem to find the mysterious Planet 9 right now. Many scientists believe this hidden world exists. They think it is lurking far beyond Neptune's orbit, but not as far away as Pluto's icy path. Our solar system can be thought of as three great neighbourhoods. First, there are the inner planets, small rocky worlds like Mercury, Venus, Earth and Mars. Then come the outer planets, the gas and ice giants like Jupiter, Saturn, Uranus and Neptune. And finally, there is the far beyond, the region of strange and distant objects still waiting to be discovered. Planet 9, if it exists, could be about the same size as Earth, or perhaps closer to the size of Mars. Long ago it may have wandered among the great gas giants, but eventually their powerful gravity flung it away, either toward the frozen outer edge of our solar system, or possibly into the dark emptiness of deep space. Jupiter itself is instantly recognizable because of its striking stripes. These colourful bands are the result of differences in temperature, the gases in its atmosphere, and the types of chemicals floating around. For a long time, scientists believed these colours were created mainly by Jupiter's intense winds and the swirling motion of gases between its atmospheric layers. Now we know there is more to the story. The pale, light-coloured stripes, known as zones, mark places where warm gas is rising upward. The darker stripes, called belts, show where cooler gas is sinking back down. The planet's many moons may even play a part in shaping these patterns. Their gravitational pull can tug at Jupiter's atmosphere, influencing the flow of its convection cells. Deep at Jupiter's heart lies a dense liquid core made of helium and a rare form of hydrogen called metallic hydrogen, along with heavier dissolved elements. The farther you move from the centre, the more the temperature and pressure decrease, until the liquid interior slowly changes into the swirling gases of the upper atmosphere. Scientists do not yet know exactly how far down this liquid gas boundary lies, but it is believed that a couple of thousand miles beneath the cloud tops, Jupiter may be almost entirely liquid. If you could somehow strip away Jupiter's thick blanket of gases, it would still be larger than some other gas giants such as Saturn. Some even call Jupiter a failed star. That name is not completely accurate, but there is a reason for it. Like real stars, Jupiter is made mostly of hydrogen. However, it is far too small to ignite the powerful thermonuclear reactions in its core that would make it shine like the sun. In theory, any object can become a star if you give it enough extra mass. With enough weight pressing inward, the temperature and pressure at its centre would rise until nuclear fusion begins. To turn Jupiter into a star like our Sun, it would need to be about 1,000 times more massive than it is now. To become a small, cooler star, a red dwarf, it would still need roughly 80 times its current mass. Jupiter will not suddenly transform into a star on its own, but if many large space objects collided with it, if it ate them, so to speak, then maybe. If Jupiter ever had become a massive star, our solar system would look completely different. Its powerful radiation would have made it far harder for planets to form stable orbits, and even harder for life to develop on any world that did survive. Jupiter also holds another record. It spins faster than any other planet in our solar system. A single day there lasts only 10 hours. That is astonishing when you remember that Jupiter is more than 300 times bigger than Earth and about 2.5 times more massive than all the other planets combined. Strangely, if Jupiter gained more mass, it would not get bigger. It would actually shrink. Adding more mass would make it denser, pulling it inward under its own gravity. Even if it were 4 times more massive, it would still be roughly the same size. Now let's leave Jupiter for a moment and visit one of the most intriguing places in the hunt for alien life. Enceladus, an icy moon of Saturn. This little world hides a vast underground ocean beneath its frozen crust. Recently, scientists detected something extraordinary there: phosphorus, the rarest of the 6 essential ingredients for life. On Earth, phosphorus helps make soil fertile, but in Enceladus's secret seas, its concentration may be between 100 and 1,000 times greater than in our planet's oceans. This may be because the moon's ocean is rich in carbonates, much like fizzy soda water, which can dissolve phosphates from its rocky seabed. This finding hints that other icy moons around Saturn, such as Titan, might also have phosphorus-rich waters. Scientists are thrilled about this because phosphates, compounds containing phosphorus, are a vital part of DNA, RNA, and the membranes that protect cells. Among the 6 elements needed for life, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, phosphorus is the rarest, and now one of the best places to search for alien life might have more than enough of it. In the year 2004, the Cassini space probe made a daring journey into the dusty veil of Saturn's second outermost ring, known as the E-ring. This ring is not made of ordinary dust. Instead, it glitters with countless tiny grains of ice, which are constantly being launched into space from geysers on one of Saturn's moons. Cassini's onboard cosmic dust analyzer studied these frozen grains in incredible detail, and to the astonishment of researchers, it revealed something extraordinary: the presence of phosphorus, a vital chemical element for life as we know it. The source of these icy treasures is Enceladus, Saturn's 6th largest moon. Yet despite that ranking, it is no giant. This little world measures only about 314 miles across. To put that in perspective, Enceladus is small enough to fit comfortably inside the US state of Arizona. When Cassini first arrived in the Saturn system, astronomers expected Enceladus to be nothing more than a frozen, lifeless snowball drifting through space. But then came the surprise. Plumes of icy particles and water vapor were spotted erupting like cosmic fireworks from cracks in the moon's surface. These spectacular geysers told an incredible story. Beneath Enceladus's solid frozen shell lies a vast global ocean, hidden between its icy crust and its rocky core. Earlier studies had already hinted that this mysterious ocean might be rich in complex organic molecules, the building blocks of life. For a long time, scientists believed that phosphorus compounds, such as phosphates, would be trapped deep inside the rocky cores of icy moons, never mixing with their oceans. That is why the new findings were such a shock. By studying 305 individual ice grains from Saturn's E-ring, researchers discovered that 9 of them contained phosphates. And this was not some uncertain detection. The results were clear and unmistakable. This is important because phosphorus is an essential ingredient for DNA, cell membranes, and energy transfer in living organisms. On other worlds, its presence is far less certain. For example, a few years ago, scientists claimed to have found phosphine, a compound made of hydrogen and phosphorus, in the clouds of Venus, but no solid proof ever emerged. On Enceladus, however, there is no controversy. Phosphates truly exist there, and Enceladus is not the only icy world worth paying attention to. Astronomers have long considered Jupiter's moon Europa to be one of the best places in the entire solar system to search for extraterrestrial life. Why? Because beneath its gleaming frozen shell lies a massive saltwater ocean that may be between 40 and 100 miles deep. True, this ocean is buried under a thick crust of ice, estimated to be between 10 and 20 miles thick, but the potential for habitability remains. Even more exciting, cracks in Europa's icy surface sometimes vent plumes of water into space, much like Enceladus. These plumes could carry chemical traces from the hidden ocean, allowing future spacecraft to taste the water without drilling through miles of ice. Better still, some evidence suggests that Europa may also have shallow pools of liquid water hiding just beneath the surface, perhaps less than 1 mile down. If that is true, it would dramatically increase the odds of finding life there and make exploration much easier. Then there is Titan, Saturn's largest moon, a strange and fascinating world that in some ways feels eerily similar to Earth. Titan is smaller than our planet and has gentler gravity, yet its thick atmosphere is dominated by nitrogen, just like ours. Even more remarkable, Titan is the only other place in the solar system with lakes and rivers on its surface. But there is a twist. These lakes are not filled with water, but with liquid hydrocarbons such as methane and ethane. Beneath this alien landscape lies another mystery, a deep underground ocean of liquid water. No one yet knows whether this ocean touches the rocky layer below the ice. If it does, chemical interactions could provide energy for life, much like on Earth's ocean floors. Of course, the search for life is not limited to icy moons. In the year 2003, the European Space Agency's Mars Express spacecraft detected methane in the thin atmosphere of Mars. On Earth, most methane comes from living organisms, including famously livestock digesting food. But on Mars, the mystery deepened. Methane should linger in the atmosphere for roughly 300 years, Yet in 2006, almost all of it vanished, disappearing about 600 times faster than scientists had expected. The question remains, what, or perhaps who, produced it, and where did it go? Another Martian puzzle involves the possibility of ancient microbes lying dormant beneath the planet's surface. Underground, they would be shielded from deadly cosmic radiation, perhaps surviving for unimaginable spans of time. Laboratory experiments simulating Martian conditions revealed that certain bacteria could endure for as long as 280 million years in such an environment. That means if life ever existed on Mars, its traces could still be waiting underground, locked away in the frozen soil. Today, the Martian surface is cold and dry, with no flowing liquid water. The temperature is so frigid it rivals that of dry ice. Any living cells on the surface would quickly freeze solid and dry out. But deep below, in pockets of ice or briny water, there could still be a record of life's ancient presence, waiting for us to dig it up. If we search every corner of our own solar system and still find no sign of the life beyond Earth, our next best hope lies far away, on worlds called exoplanets. These are planets that orbit stars outside our own star system, and some of them look remarkably promising. The closest known exoplanet to Earth is Proxima Centauri b. In cosmic terms, it is practically our neighbour, sitting a mere 4 2/10 light years away. Recently, astronomers discovered something fascinating. This alien world may be even more Earth-like than they had first imagined. Its mass is only about 17% greater than our own planet's, which means it's very similar in size and gravity. It circles a star that is smaller, cooler, and dimmer than our Sun, but it sits right in the middle of that star's habitable zone, the sweet spot where temperatures could allow liquid water to exist. But Proxima Centauri b has its quirks. It seems to be tidally locked to its star, which means one side is forever bathed in daylight, while the other side lies in endless night. Scientists are still unsure if it has an atmosphere at all. The planet swings so close to its star that it completes a full orbit, a year, there, in only 11 Earth days. But this closeness has a price. Powerful radiation from the star may be stripping away any air it once had. Without an atmosphere, liquid water would have little chance of surviving on its surface, making life there far less likely. Another intriguing world is Gliese 832c, found 16 2/10 light years from Earth, a short hop by galactic standards. This planet is a super-Earth, weighing in at about 5 times the mass of our own planet. It orbits much nearer to its parent star, completing a year in just 36 days. Yet its star is a cool, dim red dwarf, so Gliese 832c actually receives about the same amount of light and heat as Earth. Still, it may not be the gentle, life-friendly world we hope for. Scientists think it might have a thick, heavy atmosphere that triggers a runaway greenhouse effect, a dangerous process where a planet traps more heat than it can release, turning it into a sweltering oven. If that's true, Gliese 832c would be more like Venus, with crushing heat and thick clouds than the mild blue world we call home. Now, imagine this. You're piloting your sleek galactic space cruiser through the darkness, heading toward Outpost 52 with a shipment of supplies for its small scattered colony. Suddenly, warning alarms begin blaring. You glance at your displays, but before you can work out what's wrong, something outside grabs your attention. The entire front of your ship is built from transparent alloy, a one-way window to the cosmos, and through it you see a breathtaking, terrifying sight. A colossal cloud of orange and purple plasma is sweeping toward you like a tidal wave of light. There's no time for analysis. You push your ship into the steepest dive it can manage. The alarms shriek louder, the hull rattles so violently you fear it might tear apart, but your vessel is fast and powerful. Against all odds, you slip beneath the roaring cloud just in time. You watch it soar past, glowing like a living storm. Curiosity takes hold of you, and you decide to follow. Your ship's computer begins its analysis, and when the results come in, you can barely believe what you're seeing. This is no ordinary plasma cloud. It's a galaxy wrecker. Back on Earth, when you were a young pilot in training, you studied ancient research from the 21st century. Astronomers had long puzzled over why some galaxies mysteriously stopped forming new stars, fading away before their time. They knew that stars are born in cold, dense clouds of gas. Over millions of years, these clouds collapse under their own gravity, eventually igniting into brilliant new suns. One of the most famous images from the Hubble Space Telescope captures this process. The legendary Pillars of Creation in the Eagle Nebula, a vast star nursery where new stars are coming to life. But lurking in the dark are forces that destroy these cradles of light. The thing you are chasing is one of them, a giant sweeping plasma wave, rushing into young galaxies and stripping them of the very gas needed to form new stars. It's like a broom that doesn't clean. It clears away the raw material of creation itself, choking off the birth of future suns. The result is the premature death of entire galaxies, snuffed out before they can grow old. The star wrecker is no ordinary cosmic force. It is clever, patient, and knows exactly where to lurk, around enormous clusters of galaxies. One of its favourite hangouts is the Great Virgo cluster, a colossal gathering of galaxies that astronomers have been watching closely. The Virgo cluster is a giant in every sense. It stretches across a mind-bending 7 million light-years from one side to the other and contains thousands of galaxies. And when scientists call it nearby, they mean in galactic terms. It is about 65 million light-years away from us. That's far too long a trip for any weekend space cruise, but in the vastness of the universe, it's practically our neighbour. This entire cluster hurtles through a sea of superheated plasma at speeds of up to 1 million miles an hour. The Virgo cluster is part of an even larger family, the Virgo supercluster, and our own local group of galaxies, which includes the Milky Way, belongs to this same sprawling structure. Its closeness means scientists can study it in much greater detail than many other faraway regions. And it is no ordinary patch of the cosmos. It is one of the most extreme and energetic places we currently know about. It is also a bit of an oddball because, unlike many other ancient clusters, it is still giving birth to new stars. The famous Hubble nursery photograph captured some of this stellar creation in action. Among the cluster's residents is one very special galaxy, Messier 87, or M87 for short. It was first spotted in the year 1781 by the French astronomer Charles Messier. When he saw it through his telescope, it looked fuzzy and cloud-like, so he assumed it was a nebula, a cloud of gas and dust without stars. For more than a century, no one could figure out exactly what it was until the 1920s, when astronomy took great leaps forward. Charles Messier himself had quite a life. Born in rural France as the 10th of 12 children, he became fascinated with the heavens as a boy. When he was 14 years old, he saw something unforgettable, a brilliant comet with 6 tails blazing across the night sky in 1744. It shone so brightly that it became known as the 6th brightest comet in recorded history, and it remained visible to the naked eye for several months. 4 years later, on the 25th of July, 1748, young Charles watched a solar eclipse from his hometown. From that moment, he knew his life would be devoted to exploring the stars. Over his career, he discovered 13 comets, and his name now lives on in both a lunar crater and an asteroid. But none of his finds could match the sheer scale of Messier 87. This galaxy is a supergiant elliptical galaxy containing not billions but trillions of stars. It is the second brightest galaxy in the northern part of the Virgo cluster, and a favourite target for both professional astronomers and amateur stargazers. Elliptical galaxies like M87 are generally made of older, dimmer, low-mass stars, with very little new star formation. They're often surrounded by huge swarms of globular clusters, and in the Virgo supercluster, such galaxies make up about 10 to 15% of the total population. At the heart of M87 lurks a monster, a supermassive black hole. In 2017, the Event Horizon Telescope, a network of radio observatories all around the world working together as one giant virtual telescope, collected the data that would make history. In 2019, scientists proudly revealed the very first photograph of a black hole's shadow, and it was M87's. Then, in March 2021, they released a new, even more remarkable polarized image that revealed the black hole's magnetic fields in stunning detail. Other advanced observatories, like the Atacama Large Millimeter Sub-Millimeter Array in Chile, have captured breathtaking high-resolution images of 51 major galaxies in the Virgo cluster, adding to our understanding of these cosmic giants. To the naked eye, galaxies like Methane-based seem calm and still. In the span of a human lifetime, they barely appear to move at all. But in truth, they are alive with activity. Clouds of gas, drifting dust, and countless stars, all moving under the pull of gravity and the mysterious influence of dark matter, which is thought to be about 5 times more common than the matter we can see. Dark matter forms invisible halos around galaxies, and its gravitational pull can toss smaller galaxies around like toys. And this is where the star wrecker comes in. As galaxies move through the cluster, they plough into vast clouds of intergalactic plasma, a kind of electrically charged gas that can act like an atmosphere. This plasma can sweep the gas right out of a galaxy, stealing the very material it needs to make new stars. Scientists call this process gas stripping, or more technically, Ram pressure stripping. Imagine a giant cosmic leaf blower tearing through a galaxy, blowing away its precious gas into the void. This is no gentle process. A scientist from the National Research Council of Canada explained that galaxies are racing through such hot plasma so quickly that cold molecular gas is ripped away in staggering amounts. Without this gas, star formation grinds to a halt, leaving galaxies like M87 to age quietly, without new generations of stars. It is one of the most dramatic and violent acts that can happen to a galaxy, and in the Virgo cluster, it is happening on a grand scale. Watching it from a safe distance is awe-inspiring, but it is also a reminder of the raw, untamed forces that rule our universe. In the early years of the 21st century, a fascinating study uncovered something unexpected. Scientists discovered that the same strange process that occurs in enormous galaxy clusters also happens in much smaller gatherings of galaxies, sometimes with just a handful of members and with far less dark matter involved. To make this discovery, the researchers examined a jaw-dropping 10,567 satellite galaxies. These satellite galaxies are the loners of the cosmos, drifting just beyond the reach of the massive galaxy clusters, yet still living in the gravitational pull of larger neighbours. The surprising truth is that most galaxies in our universe do not live alone. Instead, they tend to gather in little families, anywhere from as few as 2 to as many as 100 galaxies in a group. But how do you study thousands of faint, distant galaxies without spending centuries staring at the sky? The trick lies in a method called stacking. This is where scientists take all the data from these dim objects, combine it, and create an average profile. Like blending thousands of faint whispers into a single clear voice, stacking allows astronomers to see patterns that would otherwise remain hidden in the cosmic static. And what did they find? It seems that gas stripping, sometimes nicknamed star wrecking, might be one of the main ways galaxies are robbed of their ability to create new stars. It's as if their galactic neighbourhoods are bullies, pulling away the raw materials they need for life and leaving them cold and quiet. A rather unpleasant way to go, like having a nasty neighbour who keeps stealing your food until you starve. But enough of this grim fate. Your curiosity is satisfied for now, and it's time to leave this drifting plasma cloud. The cruiser swings around to head for Outpost 52, and you realise you might already be late, and that could mean a heap of trouble waiting for you. While your ship changes course, let's take a leap, not just across space but across time, back to 1744, to a quiet night in rural France. There, a young teenager stands in a moonlit field, eyes wide and heart racing, watching the heavens blaze with the rare and spectacular sight of a comet with 6 shimmering tails. In that moment, under the cold brilliance of the stars, a question blooms in their mind. Perhaps the greatest question anyone can ask. What's out there? Now picture yourself standing in a sealed room full of explosive gas. One tiny spark could blast the doors and windows apart, sending a roaring pillar of fire into the night. How about visiting the largest chamber of explosive gas in our entire solar system? Jupiter, the 5th planet from the Sun, and the undeniable giant among worlds. This behemoth is 11 times wider than Earth and is almost 2.5 times heavier than all the other planets in the solar system combined. Put it on a cosmic scale, and you'd need about 317 Earths just to balance it out. Jupiter's swirling atmosphere contains a huge amount of methane, the same flammable gas that we burn in kitchen stoves or pump into certain car engines. In the ordinary, everyday universe, hydrogen is the lightest element we know. It's the featherweight champion of all matter. But over on Jupiter, hydrogen behaves very differently. That's because on this enormous planet, the pressure is unbelievably high, more than 400 million times stronger than the air pressure you feel here on Earth. To put it into perspective, Earth's air pressure is just 1 atmosphere. Now imagine multiplying that by 400 million. Under such crushing force, hydrogen becomes so squashed and compressed that it changes into something extraordinary. It turns into a shimmering liquid metal. This metallic hydrogen is not just strange, it could also be an incredibly powerful fuel. In fact, it could release about 20 times more energy than burning normal hydrogen. In other words, if you somehow carried it around, you and your matchbox could have quite a dramatic afternoon. But before we start daydreaming about lighting fires on Jupiter, we run into our first problem, getting there. Jupiter may be only 1 planet away from us in the solar system, but the journey is far from simple. Between Mars and Jupiter lies the asteroid belt, a vast cosmic minefield filled with gigantic chunks of rock. Many of these space boulders are so huge that they can be as wide as the distance from Los Angeles to Las Vegas. Some are the size of entire states. And then there's the biggest one of all, Ceres, which is almost as wide as the entire US state of Alaska. Ceres is so large that scientists officially call it a dwarf planet. Making your way through this dangerous region is no joke. Even after that, the trip to Jupiter takes about 650 days, nearly 2 years trapped inside a spaceship. For comparison, the longest time astronauts have ever stayed in space in a single mission is 84 days. Fast forward 2 years into the future, you've finally arrived. In your mind's eye, you picture striking a match on Jupiter's surface and watching the whole thing go up like a gigantic balloon. But hold on, approach with caution. Jupiter is so massive that its gravity is about 3 times stronger than Earth's. You would feel much heavier here. The match in your hand would seem weightier, your legs would feel sluggish, and jumping would be nearly impossible. And then there's the real kicker. Jupiter doesn't even have a solid surface. It's a gas giant, which means that if you tried to land, you'd just keep sinking deeper and deeper into thickening layers of gas and clouds. The deeper you go, the greater the pressure becomes, until the gases eventually turn into strange, dense liquids. Still, closer to the upper layers, you might find lighter gases such as methane. So, you think, this is it, the perfect fuel. You strike a match once, nothing. You try again, and again, still nothing. You even take out a gas burner from your pack, crank it up to maximum, and still no flame. The reason is that fire needs 3 things: fuel, an ignition source, and oxygen. Jupiter has fuel in abundance. Methane and metallic hydrogen could, in theory, blow the planet apart in seconds. You've got your ignition source, the match, but oxygen, that's the missing piece. Without oxygen, fire simply cannot burn. Think of it this way. Light a small candle on Earth, then cover it with a glass. The flame will burn for a few seconds, then go out. The fuel is still there, but the oxygen is gone. And so is the fire. Jupiter is exactly the same, only on a much, much bigger scale. We actually didn't need to make the trip to find this out. From Earth, we can watch countless meteorites, thrown out from the asteroid belt, crashing into Jupiter. As they enter its thick atmosphere, they start to burn, but they never ignite the planet as a whole. Still, if you truly wanted to make Jupiter burn, there is one terrifying way: by triggering a thermonuclear chain reaction. That would require detonating an enormous nuclear device deep within the planet. But even if we sent every nuclear bomb on Earth, it wouldn't be enough. Big asteroids already hit Jupiter with far more energy than anything we can create. For example, in the year 2009, a meteorite the size of 5 soccer fields slammed into Jupiter, unleashing an explosion equal to 5 billion tons of TNT. The blast left a dark scar on the planet as large as the Pacific Ocean. And in the year 1994, an even bigger collision left a mark nearly the size of Earth itself, though Jupiter's fierce winds erased it within weeks. Here's the real problem. Most of these explosions happen in the upper layers of Jupiter's atmosphere. To actually destroy the planet, a blast would need to reach deep into its core where metallic hydrogen is stored. If such a charge went off on something as massive as our Moon, the chain reaction could tear Jupiter apart in seconds. But the consequences would be catastrophic. Jupiter's destruction would throw the entire solar system into chaos. Earth's orbit might shift so much that the sun could rise in the west one day, or even from a completely different direction. A shock wave from the blast would strip away Earth's protective ozone layer, leaving us defenseless against the sun's deadly radiation. Eventually, asteroids from the now unstable asteroid belt would begin raining down on Earth in endless meteor showers. And here's the chilling truth: no one would be left to watch them. Jupiter's explosion would be like a miniature supernova. In fact, Jupiter is already a sort of failed star. If it were only about 50 times more massive, it would ignite on its own and become a small star called a brown dwarf. But for now, it remains what it is, the mighty gas giant of our solar system. Maybe instead of trying to blow it up, we should simply admire it from afar, or, if we're feeling adventurous, take our matches to one of the other gas giants and see what happens there. Saturn's atmosphere is a lot like Jupiter's, thick, swirling, and made mostly of gases. But just like Jupiter, it has one major problem if you're thinking about lighting a campfire. There's no oxygen there to feed the flames. Without oxygen, even the biggest box of matches in the universe won't help you start a blaze. All you can really do is stand back, take in the breathtaking sight of Saturn's shimmering rings, and move along. Uranus and Neptune are a different story. They are much smaller than Jupiter and Saturn, and they don't have metallic hydrogen deep inside them, so even if they could explode, the blast would not be as strong. But again, they share the same oxygen problem. No air you can breathe, and certainly no atmosphere you can ignite. Yet, there is one special planet where a match might actually work. Its name is GJ 1132b, and it lives about 39 light-years away. Scientists believe it might have oxygen in its air. It's not a huge gas giant, but a rocky world where you could, in theory, sit on the ground, strike a match, and watch a little fire dance as you enjoy an alien sunset unlike anything on Earth. Now, picture something very different: a frozen ancient world. It has been around for about 4.5 billion years, barely warmed by the faint rays of the distant sun. Its surface is hidden beneath a thick crust of ice. This world is smaller than our moon, yet slightly larger than Pluto. Its name is Europa, the 6th moon of Jupiter and one of the largest satellites in the entire solar system. And here is the most fascinating thing about Europa: it may be home to life. Astronomers believe it is one of the most promising places in the solar system to search for living organisms. Why? Because beneath that ice lies an enormous saltwater ocean, possibly between 40 and 100 miles deep. The ocean is hidden under a shell of ice that could be anywhere from 10 to 20 miles thick, yet it is still considered potentially habitable. Sometimes jets of water burst through cracks in the ice, spraying bits of the ocean out into space. That means some of the Europa's secrets might be drifting right above its surface, waiting to be caught by a passing spacecraft. Of course, getting down into that deep ocean would be a serious challenge. But here's the exciting part. Scientists think there may be much smaller pools of liquid water tucked just beneath the surface, perhaps less than a single mile down. That would make it far easier for future missions to explore and check for signs of life. This idea came about by pure luck. Riley Coburg, the scientist leading the study, happened to see a colleague's presentation that showed pictures of double ridges on Europa's icy crust. Coburg immediately recognized something familiar. He had seen ridges just like these here on Earth. On our planet, such features are rare, but on Europa, they are everywhere. On Earth, double ridges form when water inside an ice sheet melts and then freezes again under high pressure, pushing the ice upward in two parallel peaks. If the same process is happening on Europa, it would be strong evidence that shallow liquid water exists there. We still don't know how the ice behaves in Europa's unique environment, where the temperature, pressure, and chemistry are very different from Earth's. We can't yet measure exactly how deep or large these pockets of water might be, or how long they stay liquid before freezing over again. But one thing seems fairly clear: water beneath the ice would be shielded from Jupiter's harsh radiation, which makes the chances of a life there even higher. Europa's ocean appears to be salty too. The reddish streaks on its surface might get their colour from strange frozen mixtures of water and salts, unlike anything found on Earth. The yellowish patches, on the other hand, could be caused by sodium chloride, ordinary table salt. In laboratory experiments, scientists recreated Europa-like conditions with water, salt, extreme cold, and high pressure, producing a new kind of solid crystal. This exotic material might exist both at the bottom of the Europa's ocean and on its frozen surface, many mysteries remain, but help is on the way. Around the year 2030, NASA plans to send the Europa Clipper mission to conduct multiple close flybys and search for signs of life. The European Space Agency is also sending its JUICE mission, short for Jupiter Icy Moons Explorer, which will visit Europa within the next few years. Europa, however, is not the only possible cradle of life in our solar system. In the year 2003, the European Space Agency's Mars Express spacecraft detected methane in Mars' thin atmosphere. On Earth, most methane comes from living creatures, even something as simple as cows digesting grass. Scientists found that methane remained stable in Mars' atmosphere for roughly 300 years. Then, in the year 2006, it almost completely vanished, disappearing 600 times faster than models predicted. One of the most fascinating mysteries about Mars is the possibility that tiny life forms, microbes, might be sleeping deep under its surface. If they are there, they could have been hiding from deadly space radiation for millions upon millions of years. To test this idea, scientists recreated Martian conditions inside a laboratory. The results left them stunned. Certain bacteria could survive in those harsh conditions for as long as 280 million years. This means that if life ever existed on Mars, there's a real chance we could still find traces of it hidden underground. All we would need to do is drill deep into the Martian soil to search for these ancient survivors. Right now, there is no flowing water on the surface of Mars. Any living cell or spore there would quickly dry out. The temperature on the surface is also incredibly cold, similar to that of dry ice, turning the planet into a frozen desert. Even so, scientists believe there could be as many as 6 types of hardy bacteria or fungi living far below the surface. The toughest of them has been nicknamed Conan the Bacterium because it can endure conditions that would destroy almost anything else. Now let's leave the red planet and turn to a very different world, Venus. In the year 2020, scientists made an announcement that caused a stir. They had detected something in Venus's thick, poisonous atmosphere that might hint at life, a chemical called phosphine. This was exciting because phosphine can sometimes be created by microbes. Phosphine is a gas made of 3 atoms of hydrogen and 1 atom of phosphorus. It is highly toxic to life that needs oxygen, like humans. On Earth, it's usually found in places with little or no oxygen, such as marshes and swamps, where it's produced by special bacteria. It can also be manufactured in factories. Here's the strange part. Phosphine should not exist in Venus's atmosphere at all. The gas needs very specific conditions to form, such as high pressure, the right temperature, and a lot of hydrogen. You might expect to find it on huge gas planets like Jupiter or Saturn, but on Venus? Completely unexpected. Small amounts could be made during volcanic eruptions, lightning storms, or when meteorites strike the planet, but not nearly enough to match what scientists thought they had detected. This mystery led some researchers to dream about the possibility of alien microbes floating high above Venus's surface. But even if such organisms existed, how could they survive there? On Earth, some microbes can live in water with an acidity of about 5%, but that's their limit. The clouds of Venus are over 90% sulfuric acid, far more deadly. The air is also 50 times drier than the driest desert on Earth. And then, in the year 2022, with better, sharper telescopes, scientists concluded that there was either no phosphine at all or only a tiny trace. So, the search for life continues, this time further from Earth. Let's jump to Jupiter, the giant of our solar system. This planet is so huge that it is 318 times more massive than Earth, and more than 2.5 times heavier than all the other planets in our solar system combined. Here's an odd fact. If Jupiter were somehow made more massive, it would actually become smaller. That's because the extra weight would squeeze it tighter, making it denser without increasing its size. Scientists believe Jupiter could have up to 4 times its current mass and still be the same size. Jupiter also spins faster than any other planet. It takes only 10 hours to complete 1 full turn on its axis, and it gets hit by space rocks more often than anywhere else. Amateur astronomers have spotted strange flashes in Jupiter's clouds, signs of massive impacts. One of the most famous collisions happened in the year 1994, when a comet named Shoemaker-Levy 9 broke apart and smashed into Jupiter. The original comet was about the size of the asteroid that wiped out the dinosaurs on Earth, but before it hit, it split into more than 20 pieces. These impacts left dark scars on Jupiter's atmosphere that lasted for months. 15 years later, in the year 2009, astronomers spotted a black mark the size of Earth on Jupiter. It was left by an asteroid around 650 to 660 feet long. For comparison, the largest known asteroid to hit Earth struck Tunguska, Russia, in the year 1908. It caused a gigantic explosion, even though no crater was ever found. Why does Jupiter seem to be such a magnet for space objects? That's a mystery scientists are still trying to fully understand. In the year 1877, an American astronomer named Asaph Hall made a remarkable discovery. While studying the red planet Mars, he spotted two tiny moons circling it, Phobos and Deimos. Now, here's something fascinating. Every single planet in our solar system is named after gods and goddesses from ancient Greek and Roman mythology. Mars, also known as Ares in Greek myth, was the fierce god of war. And in those old tales, Ares had two sons, Phobos, whose name means fear, and Deimos, meaning terror or dread. It is from these unsettling names that the moons inherited their titles. Quite poetic and a little creepy. Nearly a century later, in the year 1971, NASA's Mariner 9 spacecraft sent back the very first photographs of these moons. What scientists saw surprised them. These little worlds looked nothing like our moon. They were oddly shaped, with strange, unstable orbits. In fact, no other moons in the entire solar system travel so close to their parent planet as Phobos and Deimos do to Mars. You might think that being so near, they would dominate the Martian sky. But if you were standing on Mars, you would be disappointed. The planet's curve hides them from view in many places. Even at the equator, Phobos would look to you like a small lumpy asteroid drifting past, while Deimos would be just a faint point of light, like an ordinary star. This is because, compared to our moon, they are absolutely tiny, the smallest and dimmest moons known in the whole solar system. The irony is almost funny. Despite their mighty names, they are mere crumbs in cosmic terms. For a long time, scientists thought their story was simple. The two moons were twins, much like their mythical namesakes. But then NASA's Viking orbiter sent back sharper photographs, and a big difference between the two became obvious. The entire surface of Phobos was covered with enormous grooves, deep elongated trenches running from one side to the other. Some were up to 12 miles long and 200 meters wide. Even stranger, some grooves crossed over others, proving that they didn't form all at once but during multiple events spread out over time. So what happened to Phobos? The mystery drew scientists in. Normally, astronomers can read the history of space objects by studying their scars, craters, cracks, and scratches, which act like time capsules, telling the story of cosmic events from billions of years ago. But these grooves were unusual. Other moons had a few, but Phobos was completely covered in them. The search for answers began. Phobos has a massive crater nearly 6 miles wide, named Stickney Crater, after Angeline Stickney, the wife of Asaph Hall. It seemed logical to think that a large asteroid once slammed into Phobos, blasting out the crater and creating the grooves. But this idea quickly ran into a problem. The grooves didn't radiate outward from the crater as expected. Instead, they began beside it, as if the impact wasn't the real cause. Plus, it didn't explain the intersecting grooves. Coincidence? Scientists doubted it. Another idea was that something smashed into Phobos, hurling rocks into space. Some of these fragments may have drifted away forever, but others could have been pulled back by Phobos's weak gravity, slamming into its surface again and again over thousands or even millions of years. This could explain why the grooves crossed over each other. The impacts happened repeatedly in different places. It was a neat theory, but it also had a flaw. If this were true, chunks of that debris should still be lying around Mars or its moons, or at least buried under dust on Phobos itself. Yet no such evidence has been found. Perhaps the grooves had nothing to do with Stickney Crater at all. Maybe the force came from Mars itself. Some scientists think that Phobos and Deimos were never pieces of Mars, but captured asteroids that wandered too close. NASA's Mars Global Surveyor found that the moon's chemical makeup matches that of certain meteorites and asteroids, not the rocks of Mars. If this is true, then Mars may be slowly tearing Phobos apart with its gravity, pulling on it so fiercely that the moon's surface cracks into those deep trenches we see today. And so, the mystery remains. Phobos, the moon of fear, still hides its full story, a riddle from the ancient past that may also hint at its future fate. Someday, it may spiral so close to Mars that it breaks apart entirely, scattering its remains into a ring around the red planet, a final chapter worthy of its dark and dramatic name. Far out in space, between the orbits of Mars and Jupiter, there lies a vast asteroid belt, a kind of cosmic junkyard filled with countless rocky bodies, leftovers from the early days of our solar system. Many scientists believe that the two tiny Martian moons, Phobos and Deimos, may have once belonged to this belt. Long ago, these two misshapen little worlds might have been drifting peacefully among the asteroids, but at some point in ancient history something changed. Perhaps a collision or a gravitational nudge sent them hurtling out of the belt. Eventually the pull of Mars' gravity caught them, dragging them into orbit around the red planet. This process is known as asteroid capture, and while it is not exactly rare, the case of Phobos and Deimos is baffling. Normally captured asteroids do not stay in such neat and stable orbits for very long, yet these two have been circling Mars for billions of years without drifting away. Even stranger, Mars has an extremely thin atmosphere, which makes capturing any asteroid very unlikely in the first place. In theory, the moment the conditions were right, Phobos and Deimos should have slipped away and gone back to roaming the solar system, but instead they remained stuck, as if Mars had them in an unbreakable grip. And here's where the story takes a dark turn. If this theory is correct, Mars is not just a captor, it is a destroyer. Evidence from the surface of Phobos shows long, mysterious grooves, marks that scientists think could be caused by tidal forces, the same type of gravitational tug-of-war that Earth and its moon share. The difference is that Phobos orbits much closer to Mars than our moon does to Earth, so the gravitational strain is far, far stronger. In fact, Mars is slowly tearing Phobos apart. Every 100 years, the doomed moon spirals about 7 inches closer to its parent planet. At the same time, it shrinks by about 6.5 feet, becoming weaker and more fragile with each passing century. The smaller and weaker it gets, the more those tidal forces stretch and crack it, carving strange scars across its surface. This slow-motion destruction will not last forever. In somewhere between 30 million and 50 million years, Phobos will reach its tragic end. It will either crash into the surface of Mars in a fiery impact or be ripped apart entirely, scattering into countless small fragments. If the second fate comes to pass, Mars will briefly wear a spectacular new set of rings, much like the ones now circling Saturn and Neptune. This grim destiny has earned Phobos the nickname, the doomed moon of Mars. Of course, these ideas are still theories, but they reveal just how dynamic and dramatic the lives of extraterrestrial objects can be. The more we study them, the more we uncover hidden clues about the history not only of Mars, but also of our entire solar system. And if humanity ever sets up permanent colonies on the red planet, learning the secrets of its moons could be vital for survival. Perhaps the upcoming Martian Moons Exploration mission, the MMX, will finally peel back the veil and show us the most closely guarded secrets of Phobos and Deimos. Until then, the story of Mars' tiny companions remains one of the most intriguing mysteries in planetary science. Titan is the biggest moon that belongs to the planet Saturn, and it is also the second biggest moon in the entire solar system. What makes Titan truly special is that it is the only moon we know of that has a thick atmosphere denser than Earth's atmosphere. In fact, Titan is the only place in space besides Earth where scientists have found strong proof that stable liquids actually exist on the surface. Titan is one of 7 large moons around Saturn that have enough gravity to be shaped into almost perfect spheres. Among these, it is the second farthest away from Saturn. People often describe Titan as a moon that acts almost like a planet. It is 1.5 times wider than Earth's moon and weighs about 80% more. When compared to all moons in our solar system, Titan is the second biggest, only smaller than Ganymede, a moon of Jupiter. Interestingly, Titan is even bigger than the planet Mercury in size, but it is less heavy, only about 40% as massive as Mercury. This is because Mercury is made mostly of heavy iron and rock, while much of Titan is made of lighter ice. Titan was discovered long ago in the year 1655 by a Dutch astronomer named Christian Huygens. It was the very first moon ever found around Saturn, and the sixth moon known to humans after Earth's moon, and Jupiter's 4 big moons discovered by Galileo. Titan orbits Saturn at a distance of about 20 times Saturn's radius, which is around 1,200,000 kilometers above what looks like Saturn's surface. If you were standing on Titan and looking up at Saturn, ignoring Saturn's beautiful rings, Saturn would appear to cover an angle of about 5 degrees in the sky. That means Saturn would look more than 11 times wider across than how the Moon looks from Earth, where the Moon covers less than half a degree. Titan is mostly made of a mix of ice and rock. At its centre, there is a rocky core surrounded by several layers of ice. This includes an outer crust made of a form of ice called Ice E, and beneath that there is a hidden layer of liquid water mixed with ammonia. For a very long time, Titan's thick, cloudy atmosphere stopped scientists from seeing what its surface looked like, much like how Venus's thick clouds hid its surface until recent space missions. Everything changed when the Cassini-Huygens mission arrived in 2004. This mission sent a spacecraft to explore Saturn and its moons, revealing amazing details about Titan. Scientists discovered lakes made of liquid hydrocarbons, chemicals related to methane and ethane, especially near Titan's poles. They also found that Titan's atmosphere spins faster than the Moon itself, a strange effect called superrotation. Titan's surface looks quite young and smooth, with very few impact craters. There are also mountains and some possible cryovolcanoes, which are volcanoes that erupt icy materials instead of molten rock. Titan's atmosphere is mostly made of nitrogen and methane gases. There are also small amounts of other chemicals that create clouds of hydrocarbons, and thick orange haze made of complex molecules containing nitrogen and carbon. Titan's weather includes wind and rain that shape its surface, creating features similar to Earth's deserts, rivers, lakes, and seas. These lakes and seas probably hold liquid methane and ethane instead of water. The climate changes with seasons, just like on Earth. Because Titan has liquids both on the surface and underground, plus a thick nitrogen atmosphere, its methane cycle is very much like Earth's water cycle, though much colder. Temperatures on Titan are around 94 Kelvin, which is about minus 179 degrees Celsius, or minus 290 degrees Fahrenheit. Thanks to all these similarities, Titan is often called the most Earth-like world in the solar system. Let's talk a little more about the discovery. Christian Huygens, the Dutch astronomer, found Titan on March 25, 1655. He was inspired by Galileo's discovery of Jupiter's 4 largest moons in 1610 and by improvements in telescope design. Around 1650, Huygens and his older brother, Constantin Huygens Jr., started building their own telescopes. Using one of these, Christian spotted the first moon circling Saturn. At first, Huygens called the moon Saturni Luna, which means moon of Saturn in Latin. He published his findings in a paper named De Saturni Luna Observatio Nova, which translates to a new observation of Saturn's moon, in the same year. Later, an Italian astronomer named Giovanni Domenico Cassini discovered 4 more moons orbiting Saturn between 1673 and 1686. After these discoveries, astronomers began numbering these moons from Saturn I to Saturn V, with Titan originally listed as the 4th. Other early names for Titan included Saturn's ordinary satellite. Today, the International Astronomical Union, which officially names celestial objects, calls Titan Saturn Zix. The name Titan itself comes from the Greek Titans, giant immortal beings from mythology, and was given by John Herschel, son of William Herschel, who discovered 2 other moons of Saturn in his 1847 book titled Results of Astronomical Observations Made During the Years 1834 to 1838 at the Cape of Good Hope. Since then, many smaller moons have been found around Saturn. The big moons of Saturn, including Titan, were likely formed when the planet was very young. At that time, Saturn was surrounded by a disk of gas and dust, similar to how the planets formed around the Sun. This material slowly clumped together to make moons. While Jupiter's big moons follow very regular orbits, Titan is different because it is so dominant in Saturn's system, and its path around Saturn is a bit stretched out, or eccentric. Scientists think that the original group of moons around Saturn was more like Jupiter's, but a series of huge collisions smashed them up. These violent impacts combined to form Titan, and also created mid-sized moons like Iapetus and Rhea from the leftover debris. This rough start also helps explain Titan's unusual orbit. A study from 2014 about the nitrogen in Titan's atmosphere suggested that much of it might come from materials like those in the far-off Oort cloud, rather than from the gas and dust that formed Saturn. Titan, the largest moon of Saturn, takes about 15 days and 22 hours to complete one full orbit around its giant planet. Just like Earth's moon, Titan is tidally locked with Saturn, which means it always shows the same side to Saturn as it moves around it. Because of this, one day on Titan, the time it takes to spin once on its own axis is exactly the same length as its year, or the time it takes to orbit Saturn once. When scientists measure locations on Titan, they start at the prime meridian, a line running through the middle of the face that always faces Saturn, and measure longitudes going westward from there. Titan's orbit around Saturn is not a perfect circle, but slightly stretched out, with an eccentricity of about 0.0288. This means Titan moves a little faster when it is closer to Saturn and slower when it is farther away. Additionally, Titan's orbital path is tilted just a tiny bit, about 0.348 degrees, compared to Saturn's equator, which is the imaginary line running around Saturn's middle. Nearby there is a small and oddly shaped moon named Hyperion, which has an interesting relationship with Titan. Hyperion orbits Saturn 3 times every time Titan orbits 4 times, a pattern called a 3-to-4 orbital resonance. Scientists believe Hyperion formed in a stable spot in space, while Titan's much larger mass allowed it to absorb or push away other moons or debris that got too close. Titan itself is truly impressive in size. It has a diameter of approximately 5,149 kilometers, about 3,200 miles, which makes it about 6% larger than the planet Mercury and 1.5 times bigger than Earth's moon. Among all the objects in our solar system, including the Sun, Titan ranks as the 10th largest. Before spacecraft like Voyager 1 visited Titan in the year 1980, scientists thought Titan might be even bigger than Ganymede, Jupiter's largest moon, which has a diameter of 5,262 kilometers. This turned out to be an overestimate because Titan's thick, hazy atmosphere, which stretches 100 to 200 kilometers above its surface, made it look larger than it really is when seen from afar. When it comes to Titan's makeup, its size and mass are similar to Jupiter's moons Ganymede and Kalisto. Titan's overall density is about 1.881 grams per cubic centimeter, which tells scientists that its interior is made of roughly 40 to 60% rock, with the rest being water ice and other materials. Inside Titan, the structure is probably layered. At its heart lies a rocky core about 3,400 kilometers wide. Around this core there are several layers made up of different types of ice and possibly liquid water. The exact details of these layers depend on how much heat comes from Titan's inside, something scientists are still trying to understand well. The interior might be warm enough to have a hidden liquid layer made from a mixture of water and ammonia, sort of like a watery magma, situated between the outer icy crust and deeper ice layers made of special high-pressure ice forms. In fact, Titan might be so warm inside that the highest pressure ices can't form at all, leaving a liquid water layer just beneath the solid surface crust. Thanks to ammonia, this watery layer can stay liquid even when the temperature is as low as 176 Kelvin, which is about -97 degrees Celsius. The Cassini spacecraft, which studied Titan for many years, found clues supporting this layered interior. It detected very low-frequency radio waves in Titan's atmosphere that don't seem to bounce off the surface well. Instead, scientists think these radio waves reflect off the boundary between a hidden subsurface ocean and the ice above it. Cassini also observed that Titan's surface features shifted by up to 30 kilometers between October 2005 and May 2007, suggesting that the outer crust can move independently of the interior below. This movement supports the idea of a liquid ocean beneath the crust. Other data, such as changes in Titan's gravity as it orbits Saturn, also indicate the presence of this liquid layer and a shell of ice that isn't fully attached to the solid rocky core. When comparing gravity measurements with radar images of Titan's surface, scientists think that the ice shell is quite rigid, like a solid shell floating on liquid. Titan's atmosphere is rich in methane, a gas similar to the natural gas we use on Earth. However, methane on Titan must be constantly replenished because sunlight breaks it down over time. The source of this methane might be from inside Titan itself, released through icy volcanoes called cryovolcanoes. On April 3, 2013, NASA reported that complex organic chemicals called tholins likely form in Titan's atmosphere, based on experiments simulating Titan's conditions. A few months later, on June 6, 2013, scientists found large molecules called polycyclic aromatic hydrocarbons in Titan's upper atmosphere, compounds important in organic chemistry. Another exciting discovery came on September 30, 2013, when NASA's Cassini spacecraft detected a gas called propene in Titan's atmosphere using an instrument called the Composite Infrared Spectrometer. This was the first time propene had ever been found on any moon or planet other than Earth. It helped fill a missing piece in understanding Titan's hazy atmosphere, first studied during Voyager 1's flyby in 1980. Scientists now know many of Titan's atmospheric gases are hydrocarbons, formed when sunlight breaks apart methane molecules. Titan's surface is extremely cold, about 94 Kelvin, that is, minus 179.2 degrees Celsius. At this chilly temperature, water ice does not easily turn into vapor, so only tiny amounts of water vapor exist high in the atmosphere. Titan receives just 1% of the sunlight that Earth does, and about 90% of that sunlight is absorbed by the thick atmosphere before it can reach the surface. This means only about 0.1% of Earth's surface sunlight shines down on Titan. Methane in Titan's atmosphere creates a greenhouse effect, trapping heat and making the surface warmer than it would otherwise be. However, the thick haze in the atmosphere also causes an anti-greenhouse effect by absorbing sunlight before it reaches the surface, cooling Titan down a bit. So, Titan's surface ends up much colder than the upper atmosphere. Titan has clouds too, made mostly of methane, ethane, or other simple organic molecules. These clouds are scattered and change over time, breaking through the constant haze. The Huygens probe, which landed on Titan, found that the atmosphere sometimes rains liquid methane and other organic chemicals onto the surface. Usually, clouds cover only about 1% of Titan's visible disk, but sometimes big cloud bursts increase the coverage up to 8%. Scientists think southern hemisphere clouds form during Titan's southern summer, when more sunlight heats the atmosphere and causes air to rise, creating convection and cloud formation. But cloud formation also happens at other times, like mid-spring, which puzzles scientists. Increased humidity of methane near the South Pole might help explain sudden growth in cloud size. Until the year 2010, it was summer in Titan's southern hemisphere. But as Saturn moved in its orbit, Titan's northern hemisphere gradually moved into more sunlight. When the seasons change, scientists expect ethane gas to start condensing as frost or ice over the South Pole. Titan has a surface that scientists describe as very complex and shaped by flowing liquids and other active processes. Even though Titan itself has existed since the very beginning of our solar system, which formed about 4.5 billion years ago, its surface is much younger. Experts estimate that Titan's surface is somewhere between 100 million and 1 billion years old. This suggests that Titan's landscape has been changed and reshaped over time by natural geological forces. One of the most interesting facts about Titan is its thick atmosphere, which is about 4 times denser than Earth's atmosphere. Because of this, it is very hard to take clear pictures of Titan's surface using normal telescopes that see visible light. To get around this problem, NASA's Cassini spacecraft, which orbited Saturn for many years, used special tools like infrared cameras and radar systems to peek through the haze and map parts of Titan's surface during close flybys. The first images from Cassini showed a surface full of surprises. There are some areas that look rough and rugged, while others appear very smooth. Scientists even found possible signs of volcanoes, but these volcanoes would be very different from Earth's. Instead of erupting molten rock, Titan's volcanoes might release a mixture of water and ammonia, freezing quickly in the cold temperatures. This strange kind of ice volcano could explain some parts of Titan's surface. Titan's outer ice layer also seems quite stiff and hard in many places, which might mean that it does not have a lot of geological activity like earthquakes or mountain building in some regions. On the other hand, there are long streaks stretching hundreds of kilometers that look like they were made by wind carrying tiny particles across the surface. When scientists look carefully, Titan's surface looks fairly smooth overall. The few craters from meteor impact seem to have been partly filled in or covered up, maybe by rains of liquid hydrocarbons or by cryovolcanoes. Radar measurements suggest that most of Titan's landscape doesn't have very tall features. Usually the height differences are less than 150 meters, but sometimes Titan surprises us with hills or mountains that rise several hundred meters, or even more than 1 kilometer high. Looking at Titan's geography, we find large, bright and dark regions. One famous bright region near the equator is called Xanadu. It is huge, about the same size as the continent of Australia. Scientists first spotted Xanadu in 1994 using the Hubble Space Telescope's infrared vision, and later Cassini gave us clearer views. Xanadu is full of hills, valleys and deep chasms. It also has many winding dark lines that look like ridges or cracks. These features might mean that Titan's surface is slowly moving and cracking, a sign of tectonic activity, which would mean that this part of Titan is relatively young. Another idea is that these lines could be channels carved out long ago by flowing liquids, meaning the area might be older but has been shaped by erosion. Elsewhere on Titan, we see other large dark areas similar in size to Xanadu. One of these is called Ligeia Mare, which is the second largest sea on Titan. Unlike Earth's water seas, Ligeia Mare is made mostly of liquid methane, a simple hydrocarbon gas on Earth. After the Voyager spacecraft flew by Titan in the early 1980s, scientists learned that Titan has a thick atmosphere capable of holding liquid hydrocarbons on its surface. But the first clues to actual lakes and seas didn't appear until 1995, when data from the Hubble Space Telescope and radar showed hints of large liquid bodies. The existence of these methane and ethane seas was finally confirmed directly by the Cassini spacecraft in January 2007. The mission team proudly announced that they had found clear proof of lakes filled with liquid methane on Titan. These lakes and seas mostly gather around Titan's polar regions, where it is cold enough for liquid hydrocarbons to remain stable and not evaporate. Near the North Pole, the largest sea is called Kraken Mare, followed by Ligeia Mare and Punga Mare. Together, these three cover a huge area, about 691,000 square kilometers, which is roughly 267,000 square miles. That's close to 80% of all the liquid bodies on Titan. The levels of these seas appear to be about the same, which suggests they might be connected underground, like lakes connected by rivers on Earth. In the southern polar region, there are 4 large dry basins that might once have been seas but have dried up. There are also smaller lakes scattered around the poles, covering an area of about 215,000 square kilometers, or 83,000 square miles. Scientists have suggested that smaller lakes might exist closer to Titan's equator, or in lower latitudes, but none have been confirmed yet. Sometimes, after heavy rainstorms, temporary pools might form near the equator. Using radar from Cassini, scientists even measured the depth of some lakes. For example, Ligeia Mare is about 200 meters deep, which is roughly 660 feet. Ontario Lacus, a smaller southern lake, is about 90 meters deep, or 300 feet. Titan's lakes and seas are mostly made of methane, with smaller amounts of ethane and dissolved nitrogen. The exact mix varies. Ligeia Mare has about 71% methane, 12% ethane, and 17% nitrogen by volume, while Ontario Lacus has roughly 49% methane, 41% ethane, and 10% nitrogen. Because Titan always shows the same face to Saturn, it experiences tidal forces that create a permanent bulge of about 100 meters, or 330 feet, on the side facing Saturn and the opposite side. Titan's slightly oval orbit causes these tidal forces to change slowly over time, but the changes are gentle. Researchers led by Ralph D. Lorenz estimated that the tides in Titan's bigger seas rise and fall by about 20 to 80 centimeters, or roughly 8 to 32 inches. In July 2025, NASA scientists published a fascinating study showing that tiny cell-like compartments, called vesicles, which are necessary for the formation of the life's building blocks, could form in Titan's lakes. Astrobiologists think that the liquid hydrocarbons in these lakes might allow molecules important for life to come together. Studying this could help us better understand how life first began here on Earth. Thanks to the Cassini spacecraft's radar mapping, scientists have been able to study the surface of Titan, Saturn's largest moon, in much greater detail. This mapping revealed many landforms that several researchers believe might be signs of cryovolcanism, a kind of icy volcano activity, and tectonic processes, movements of the moon's icy crust. In 2016, a study focused on the mountain ridges found on Titan showed that these ridges are mostly found near the moon's equator, the middle region between its poles. This suggests that ridges either form more often or last longer in these low-latitude areas. These ridges generally stretch from east to west and have shapes that range from straight lines to gentle curves. The scientists compared these ridges to similar folded mountain belts on Earth, which form when the ground is squeezed horizontally. The way these ridges are spread around Titan hints that the entire moon might be slowly shrinking or contracting. This contraction could cause the ice shell covering Titan to thicken and push up parts of the surface. When it comes to identifying signs of cryovolcanoes on Titan, things are still uncertain and debated. The main reason is that Cassini's images and data, though impressive, have limitations in how clearly and completely they cover Titan's surface. Still, radar and visual imaging from Cassini have spotted several possible cryovolcanic features. For example, in the western part of a region called Xanadu, there are flow-like areas that look like they might have been formed by icy lava. Also, in Titan's northern hemisphere, there are some steep-sided lakes that look similar to Mare craters on Earth. Mare craters form on Earth when underground explosions push up the surface. Among these possible icy volcanoes, one complex of landforms stands out. It includes two mountains called Doom Mons and Erebor Mons, a large depression named Sotra Patera, and a system of flow-like formations called Mohini Fluctus. Interestingly, between 2005 and 2006, parts of Sotra Patera and Mohini Fluctus became noticeably brighter, while the nearby plains did not change. This brightness change could hint that cryovolcanic activity was still happening during that time. There are also indirect clues supporting the idea that cryovolcanism is active on Titan. One of these clues is the presence of argon-40 in Titan's atmosphere. Argon-40 is a radioactive gas produced by the decay of potassium-40, a process that happens deep inside Titan's rocky core over billions of years. Because argon-40 is found in the atmosphere, it suggests there are active geological processes bringing this gas up from inside Titan to its surface, and cryovolcanism is one possible way this could happen. When we look at impact craters on Titan's surface, there are surprisingly few of them compared to other moons. Processes like erosion, tectonic shifts, and cryovolcanic activity may have erased many craters over time. Compared to moons with similar sizes and structures, like Ganymede and Kalisto, Titan's craters are much shallower. Many craters have dark floors made of sediments. Studies of the shapes and features of these craters suggest that erosion and burial by sediments are the main ways these craters change and disappear. Additionally, craters are not spread evenly over Titan's surface. The polar regions near the North and South poles have almost no visible craters, while most craters are found in the equatorial regions where sand dunes are common. This uneven distribution might be because oceans once covered Titan's poles, or because rain and sediment deposition in the past have changed these areas, or because erosion happens faster near the poles. Most of Titan's surface is covered by plains. Of these, the most widespread are called the undifferentiated plains. These plains appear as vast, smooth and radar-dark areas. They are mostly found between 20 and 60 degrees north or south of the equator, meaning in the mid-latitude regions. Scientists believe these plains are younger than almost all other major features on Titan, except for dunes and some craters. The undifferentiated plains were likely formed by winds carrying and depositing organic-rich sediments. Another very common type of terrain on Titan is sand dunes. These dunes gather into huge dune fields or sand seas, mostly within 30 degrees north or south of the equator. Titan's dunes are typically 1 to 2 kilometers wide and spaced 1 to 4 kilometers apart. Some individual dunes are over 100 kilometers long. Radar data suggests these dunes stand about 80 to 130 meters tall. In the images taken by Cassini's radar, the dunes appear dark. The way dunes interact with mountains and other obstacles shows that the sand usually moves from west to east. The sand itself is mostly made of organic material, probably coming from Titan's thick atmosphere. The sources of this sand might include river channels or the undifferentiated plains. Even though Titan is not visible to the naked eye from Earth, it can be seen using small telescopes or strong binoculars. However, it is hard to observe because Titan is so close to Saturn's bright globe and shining rings. Using an occulting bar, a small device that blocks part of the bright planet when looking through the eyepiece, helps a lot in seeing Titan more clearly. Titan's brightest apparent magnitude, which measures how bright it looks from Earth, is about plus 8.2, with an average brightness at opposition of plus 8.4. By comparison, Ganymede, a similar-sized moon of Jupiter, shines brighter at plus 4.6. Before spacecraft visited Titan, observations were limited. Back in 1907, astronomer Joseph Comas Sola noticed that the edge of Titan appeared darker, a sign that Titan has an atmosphere. Later, in 1944, Gerard P. Kuiper used a technique called spectroscopy to detect methane in Titan's atmosphere. The first spacecraft to visit the Saturn system was Pioneer 11 in 1979. It showed that Titan was probably too cold to support life as we know it. Pioneer 11 also took images of Titan and Saturn together during the middle to late parts of that year. Soon after, the Voyager missions surpassed Pioneer's images with much clearer data. Titan was then closely examined by both Voyager 1 and Voyager 2, which flew by in 1980 and 1981 respectively. Voyager 1's path was specially planned to give it the best chance to study Titan up close. It was able to measure Titan's atmosphere's density, temperature and composition, and to determine Titan's exact mass. However, thick atmospheric haze blocked clear views of the surface. Only in 2004, through careful digital processing of Voyager 1's images taken with an orange filter, did hints of light and dark surface features become visible. These features are now called Xanadu and Shangri-La, which were also observed using the Hubble Space Telescope in infrared light. Voyager 2 was ready to fly by Titan too, but ended up continuing on its journey to Uranus and Neptune instead. The Cassini-Huygens spacecraft arrived at Saturn on the first day of July in the year 2004. Once there, it began an exciting mission to map the surface of Titan, Saturn's largest moon, using powerful radar technology. This mission was a joint effort between two space organizations, the European Space Agency, often called ESA, and NASA from the United States. Together, they made Cassini-Huygens one of the most successful space missions ever. Just a few months later, on the 26th of October 2004, the Cassini spacecraft flew very close to Titan, only about 1,200 kilometers away, which is roughly 750 miles. During this close encounter, Cassini took the most detailed pictures of Titan's surface ever captured. These pictures revealed patterns of light and dark areas that are too faint for the human eye to see, showing just how mysterious and beautiful Titan's landscape really is. Then, on the 22nd of July 2006, Cassini came even closer to Titan, flying just 950 kilometers, about 590 miles above its surface. The closest flyby happened on the 21st of June 2010, at a distance of only 880 kilometers, or about 550 miles. During these passes, Cassini discovered that Titan's North Pole is dotted with many lakes and seas filled with liquid, an astonishing find that surprised scientists and made Titan one of the few places in our solar system known to have liquid on its surface. Meanwhile, the Huygens probe, which was designed to study Titan's atmosphere, made a historic landing on Titan on the 14th of January 2005. This landing made Titan the farthest place from Earth where a spacecraft has ever touched down. Huygens found that many of Titan's surface features were shaped long ago by flowing liquids, showing that this moon has been geologically active. Huygens landed near the eastern tip of a bright area now called Adiri. It took photos of pale-coloured hills with dark, river-like streaks running down to a flat, dark plain below. Scientists believe these hills, also called highlands, are mostly made of water ice. On Titan, dark organic compounds are created high in the atmosphere by the sun's ultraviolet rays, and these compounds may fall like rain, mixing with methane rain to wash down the hills and build up the dark plains over millions of years. After landing, Huygens snapped pictures of a dark plain covered with many small rocks and pebbles made of water ice. Two rocks visible near the centre of one image were actually quite small. The left one was about 15 centimetres wide, and the one next to it was just 4 centimetres wide. They were about 85 centimetres away from the probe. Scientists noticed signs of erosion near the base of these rocks, hinting that liquid might have once flowed there. The ground itself was darker than expected, and seemed to be made of a mix of water ice and frozen hydrocarbons. In March, 2007, NASA, ESA, and the Committee on Space Research, COSPAR, decided to honour the former president of ESA by naming the Huygens landing site the Hubert Curien Memorial Station. Looking to the future, a new exciting mission called Dragonfly is being developed by the Johns Hopkins Applied Physics Laboratory. This mission, planned for launch in July 2028, will send a large drone powered by a special nuclear battery called an RTG to fly through Titan's thick atmosphere. Dragonfly will explore Titan as part of NASA's New Frontiers program and is expected to arrive in the mid-2030s. Its goal is to study how far chemical processes that could lead to life, known as prebiotic chemistry, have advanced on Titan. Over the years, scientists have also dreamed up many other ideas for missions to return to Titan. NASA, ESA, and the Jet Propulsion Laboratory have all worked on early plans for new spacecraft, though none have yet been officially funded. One such idea was the Titan-Saturn system mission, a joint project between NASA and ESA. It imagined sending a hot air balloon to float in Titan's atmosphere for 6 months to study the Moon closely. However, in 2009, ESA and NASA decided to prioritize a mission to Jupiter's moon Europa instead. Another proposed mission was the Titan Mare Explorer, or TIME, a low-cost lander designed to splash down into one of Titan's large northern seas called Ligeia Mare. TIME would have floated on the liquid, studying Titan's hydrocarbon cycle, the chemistry of its seas, and the moon's origins. Although it passed an initial design study in 2011, it was not chosen to fly. In early 2012, scientist Jason Barnes from the University of Idaho proposed a small drone plane called Aviator, designed to fly through Titan's atmosphere and take sharp, high-definition images of the surface. However, NASA did not approve the requested funding of $715 million, and the project's future remains uncertain. Later in 2012, a Spanish engineering company called CINA, together with the Centro de Astrobiología in Madrid, proposed another lake lander called Talise. Unlike TIME, Talise would have its own propulsion system, allowing it to move around on the lake instead of just drifting. Another idea is the Journey to Enceladus and Titan mission, or JET, which would orbit Saturn and study the potential habitability of Titan and another of Saturn's moons, Enceladus. However, in 2015, NASA's Innovative Advanced Concepts program awarded a Phase 2 grant to a study designing a submarine that could explore Titan's seas beneath the surface. Titan, the largest moon of Saturn, is believed to be a fascinating world that might resemble the very early Earth before life began. Scientists think it is a prebiotic environment, meaning it has many complex organic chemicals that could be the building blocks of life. However, Titan's surface is incredibly cold, around -179 degrees Celsius. At this extreme cold, the surface is frozen solid, so life as we know it cannot survive there. But Titan hides a secret beneath its icy shell. Scientists believe there is a vast global ocean of liquid water deep below the frozen surface. This hidden ocean might provide conditions suitable for tiny, simple life forms called microbes. These microbes could possibly live in the warmth and shelter beneath the ice, where the temperature is much less harsh. Back in the early 21st century, the Cassini-Huygens spacecraft explored Titan closely. Although this mission was not designed to directly find signs of life or complex organic molecules, it showed that Titan's environment shares some similarities with what scientists think Earth's atmosphere was like billions of years ago, before life appeared. For example, Titan's atmosphere is rich in nitrogen and methane, similar to early Earth's atmosphere, except Titan lacks water vapor in its skies. Experiments done on Earth have helped scientists imagine how life's building blocks could form in such an atmosphere. The famous Miller-Urey experiment, and others that followed, demonstrated that when a mix of gases like those on Titan's atmosphere is exposed to ultraviolet light, complex molecules called tholins can form. These tholins are dark, sticky substances made from nitrogen and methane reacting together. The process starts when the nitrogen and methane break apart, creating chemicals like hydrogen cyanide and acetylene, which then combine into more complicated molecules. A remarkable discovery from these experiments was that 5 of the nucleotide bases, the very building blocks of DNA and RNA, could be created even without any liquid water present. Along with these, amino acids, which are the basic components of proteins, were also found. This was the first time these important molecules of life had been formed in such conditions, suggesting that the early chemistry needed for life might begin without water as a solvent. Laboratory studies suggest that Titan might have enough organic material on its surface and in its atmosphere to kickstart a chemical evolution, similar to what might have led to life on Earth. However, this idea depends on there being liquid water for extended periods beneath Titan's surface, which might happen if an asteroid or comet impact melts some of the ice and forms a subsurface ocean protected by a frozen layer above. Some scientists even think that oceans made of a mixture of water and ammonia could exist deep below Titan's icy crust. These oceans could be as deep as 120 miles under the surface. Even though conditions there would be extremely harsh compared to Earth, it is possible that some form of life could survive in such an environment. For life to continue in these hidden oceans, heat from Titan's interior would need to travel upward through the ice, keeping the water liquid. If any microbes do live there, scientists hope to detect their presence by studying the chemical signatures they leave behind, like changes in the amounts of methane and nitrogen in Titan's atmosphere. Interestingly, some researchers have suggested that life might even exist in Titan's surface lakes, which are filled not with water but with liquid methane and ethane, hydrocarbons that behave like water does on Earth. If so, these strange life forms would breathe hydrogen gas instead of oxygen, use acetylene instead of sugar for energy, and release methane instead of carbon dioxide. However, surviving and metabolizing at such an extremely cold temperature, about -179 degrees Celsius, would require very different chemistry than any life we know. On Earth, all living things use liquid water to carry out the chemical reactions of life because water is a powerful solvent and reacts easily with other molecules. On Titan, though, life might rely on liquid hydrocarbons like methane or ethane as a solvent. While water breaks down large organic molecules quickly, hydrocarbons do not, so this might help preserve the complex molecules needed for life, even if the chemical environment is very different. In the year 2005, astrobiologist Chris McKay proposed that if methanogenic life forms, that is, life that produces methane, were living on Titan's surface, they would change the amounts of certain gases in the atmosphere. Specifically, they would use up hydrogen and acetylene, causing these gases to be less abundant than expected. According to his calculations, if life there behaved like similar organisms on Earth, the amount of molecular hydrogen near the surface could be 1,000 times lower than normal. However, life on Titan would be very slow because of the freezing temperatures, unless special catalysts like enzymes helped speed up chemical reactions. Another challenge is that organic compounds dissolve poorly in methane, making it harder for life to take in nutrients. But life might overcome this by using special ways to transport chemicals, or by having a large surface area relative to volume. In 2010, researcher Darrell Strobel found that there is more hydrogen in Titan's upper atmosphere than near the surface, suggesting hydrogen moves downward and disappears somewhere close to the ground. This matches McKay's predictions if life were consuming the hydrogen. The same year, other studies showed low amounts of acetylene on Titan's surface, which could also mean organisms are using it as food. Still, scientists remain cautious. Other explanations might exist for these gas patterns, such as unknown chemical reactions or surface catalysts that remove these gases without life being involved. While finding a catalyst that works at such cold temperatures would be exciting, it would not be as surprising as discovering actual life. Mark Allen, a lead scientist at NASA's Astrobiology Institute, suggested a non-living explanation for the acetylene shortage. Sunlight or cosmic rays might break down acetylene in Titan's atmosphere, turning it into more complex molecules that fall to the surface without leaving acetylene behind. NASA's official statement from June 2010 reminds us that methane-based life forms are still only hypothetical. No one has detected such life anywhere yet, but some scientists believe these chemical clues might hint at a very primitive or unusual form of life on Titan. In February 2015, scientists created a model of a possible cell membrane that could survive and function in liquid methane at Titan's cold temperatures. This membrane, made from small molecules containing carbon, hydrogen, and nitrogen, was named an azotism, combining the French word for nitrogen, azote, with liposome, the term for Earth-like cell membranes. the exotosome membrane could be just as stable and flexible as membranes made from phospholipids here on Earth. Although there are some concerns about whether exotosomes could form naturally based on energy considerations, newer studies propose ways these membranes might indeed arise on Titan. This idea opens new possibilities for how life might look and function in environments very different from our own. Even though there are some signs that life might be possible on Titan, there are many big challenges that make it very hard for life as we know it to exist there. Titan is extremely far from the Sun, so it is incredibly cold. Unlike Earth, Titan's atmosphere does not have carbon dioxide, which on our planet helps keep it warm and supports life. On Titan's surface, water is not liquid but is frozen solid as ice. Because of these tough conditions, some scientists like Jonathan Lunine think of Titan not so much as a place where life probably exists, but more like a natural laboratory, a place where we can study what conditions might have been like on Earth before life began. Even if there is no life on Titan, the chemical environment there, full of complex organic molecules, gives scientists important clues about how life might have started here on Earth billions of years ago. To learn more about this, researchers don't just rely on spacecraft observations. They also run experiments in labs on Earth and create detailed chemical models to understand the kinds of reactions happening on Titan. There is also an interesting idea about how life could spread through the solar system. Some scientists suggest that when big asteroids or comets crashed into Earth long ago, pieces of rock containing tiny living microbes could have been blasted off into space. These pieces might have travelled and landed on other places in our solar system, including Titan. This idea is called panspermia. However, Jonathan Lunine points out that if there were any life in Titan's extremely cold lakes made of liquid hydrocarbons, it would have to be so chemically different from Earth life that it could not have come from Earth's microbes. In other words, life on Titan, if it exists, would be something completely alien. Looking much further ahead, the conditions on Titan could actually become much more friendly for life, just not anytime soon. About 5 billion years from now, the Sun will start to change as it grows into a red giant star. This change will make Titan warmer, and it might even allow liquid water to appear on its surface. If this happens, Titan could become a place where life might survive. Additionally, the Sun's ultraviolet rays will become weaker, causing the thick, hazy clouds high in Titan's atmosphere to thin out. This would reduce a cooling effect called the anti-greenhouse effect, allowing the methane gas in Titan's atmosphere to trap more heat and warm the surface further. These combined changes could create a warm, stable environment on Titan for hundreds of millions of years. That would be enough time for simple life forms to develop, similar to how life first began on Earth. However, because Titan's liquids might be a mixture of ammonia and water, which is thicker and colder than pure water, chemical reactions there would happen more slowly than on Earth. Kalisto is the second biggest moon that orbits the planet Jupiter, coming right after the largest moon called Ganymede. If we look at all the moons in our entire solar system, Kalisto ranks as the third largest, following Ganymede and Titan, which is the largest moon of the planet Saturn. In fact, Kalisto is almost as big as Mercury, which is the smallest planet in the solar system. Kalisto's diameter, meaning the distance straight through it from one side to the other, measures about 4,821 kilometers. To give you a comparison, this is roughly 1/3 larger than Earth's moon. When it comes to distance, Kalisto orbits Jupiter at an average distance of about 1,883,000 kilometers. This is around 5 times farther away from Jupiter than Earth's moon is from Earth. Kalisto is the farthest out of the 4 big moons of Jupiter, known as the Galilean moons. These 4 moons were discovered way back in the year 1610 by the famous astronomer Galileo Galilei, using one of the first telescopes ever built. Today, you can even spot Kalisto from Earth by using simple binoculars, which is pretty amazing considering how far away it is. The surface of Kalisto is truly ancient. It is the oldest and most heavily cratered surface anywhere in the entire solar system. Its whole surface is covered with countless craters, which are round holes created by objects like asteroids crashing into it over billions of years. Unlike some other moons and planets, Kalisto shows no signs of volcanic activity or the movement of its surface like Earth's tectonic plates. There is no evidence that any kind of geological activity has ever reshaped its surface. Instead, Scientists believe Kalisto's surface has mostly changed because of impacts from space debris. Some of the most noticeable features on Kalisto's surface are large multi-ring structures, which look like giant overlapping circles formed by huge impacts long ago. There are also many craters of different shapes, chains of craters called catenae, and nearby cliffs, ridges, and layers of deposits. When looking closer, the surface looks quite varied. Small, shiny frost deposits sparkle at the tops of high points, while the lower areas have smooth, dark materials covering them. This strange texture likely happens because of a process where tiny landforms slowly disappear as ice turns directly from solid to gas, a process called sublimation. This idea is supported by the fact that there are fewer small craters than expected, along with many small knobs thought to be what remains after the tiny features have vanished. Scientists don't yet know the exact ages of these surface features. Kalisto is made up of about equal parts rock and ice, giving it a density of roughly 1.83 grams per cubic centimetre. This is the lowest density and surface gravity compared to Jupiter's other big moons. Using special instruments that analyse light, researchers have found water ice, carbon dioxide, silicate minerals, which are rocky materials, and organic compounds on the surface. The Galileo spacecraft, which studied Jupiter and its moons in detail during the 1990s and early 2000s, showed that Kalisto may have a small core made of rock beneath its surface. There might also be a hidden ocean of liquid water deep inside, lying more than 100 kilometers beneath the surface. Unlike the three other large Galilean moons, Io, Europa and Ganymede, Kalisto is not caught in what scientists call an orbital resonance. This means it does not experience strong gravitational tugs from its neighbours that would heat it up through tidal forces. Because of this, Kalisto is not significantly warmed from inside. It spins in sync with its orbit around Jupiter, meaning the same side of Kalisto always faces Jupiter, just like how our moon always shows the same face to Earth. So, if you stood on Kalisto's near side, Jupiter would always be hanging in the sky right above you. Kalisto orbits farther away from Jupiter than the other inner moons, so it is less affected by Jupiter's powerful magnetic field and radiation belts. This makes it a safer place for potential future space missions. Kalisto has a very thin atmosphere made mostly of carbon dioxide gas, and it probably has some molecular oxygen as well. Surrounding it is a fairly strong ionosphere, a layer of charged particles high above the surface. Scientists think Kalisto formed slowly from the cloud of gas and dust that circled Jupiter soon after the planet itself was born. Because Kalisto gathered material slowly and did not experience much tidal heating, it never got hot enough to separate fully into layers like Earth did. Instead, slow movements of material inside it began soon after it formed, causing partial layering and possibly creating the underground ocean far below. The possible existence of this hidden ocean means that Kalisto might hold the conditions needed for some kind of life. However, compared to its neighbouring moon Europa, scientists believe conditions are less favourable for life on Kalisto. Many space missions have studied Kalisto over the years, starting with the Pioneer 10 and 11 probes, and continuing through the Galileo and Cassini spacecraft. Because of Kalisto's low radiation environment, it has long been considered the best spot around Jupiter to place future crewed spacecraft that might explore the Jovian system more closely. Kalisto was discovered independently by two astronomers, Simon Marius and Galileo Galilei, in the year 1610. They found it at the same time as the other three large moons of Jupiter, Ganymede, Io, and Europa. Like all of Jupiter's moons, Kalisto's name comes from Greek mythology. Kalisto was a nymph, or, according to some stories, the daughter of a man named Lycaon, who was closely linked to Artemis, the goddess of the hunt. The name Kalisto was suggested by Simon Marius shortly after the moon's discovery, and he said that the famous astronomer Johannes Kepler had come up with the name. For a long time, the names of the Galilean moons were not widely used and were often ignored in favour of simpler labels. In older astronomy books, Kalisto was usually called by its Roman numeral Jupiter 4, or simply the fourth satellite of Jupiter, a system originally introduced by Galileo himself. In English, there isn't one fixed adjective form for Kalisto. The original Greek form suggests some possibilities, but in practice, different versions have appeared, like Kalistoan, Kalistian, Kalistian, and others. None have become official. Unlike Earth's moon, other planetary moons never received special symbols in astronomy. However, A software engineer named Dennis Moskowitz, who designed symbols for dwarf planets, suggested a symbol for Kalisto. It combined the Greek letter kappa, the first letter of Kalisto, with part of the symbol for Jupiter, but this symbol has not become common. Kalisto is the farthest out of the 4 big moons of Jupiter that were discovered by Galileo, known as the Galilean moons. It orbits Jupiter at a very large distance of about 1,880,000 kilometers. To give some perspective, that is over 26 times farther than Jupiter's own radius, which is about 71,492 kilometers. Kalisto's orbit is much wider than the next closest big moon, Ganymede, which circles Jupiter at around 1,070,000 kilometers. Because Kalisto orbits so far away, it does not take part in the special kind of gravitational dance called mean motion resonance, which the 3 moons closer to Jupiter, Io, Europa and Ganymede, are locked into. Scientists think Kalisto probably never joined this resonance pattern. However, in about 1.5 billion years, it might finally get pulled into this rhythm, completing a chain where their orbital periods fit in ratios of 1 to 2 to 4 to 8. Like most moons that regularly orbit their planets, Kalisto always shows the same side to Jupiter. This means that its rotation, how long it takes to spin once around its axis, matches exactly with how long it takes to go once around Jupiter. Kalisto's day, the length of time for one full spin and one full orbit, is about 16 2/3 Earth days. Its orbit is almost a perfect circle, but just a tiny bit stretched out, and it's tilted slightly compared to Jupiter's equator. These small changes in shape and tilt happen slowly over hundreds of years because of the gravitational pulls from the Sun and other planets. The eccentricity, how stretched the orbit is, varies between about 0.0072 and 0.0076. The tilt angle changes between about 0.2 and 0.6 degrees. These orbital wobbles also cause the tilt of Kalisto's spin axis, the angle between its rotation and orbit, to shift between 0.4 and 1.6 degrees. Because Kalisto is so far from Jupiter and isolated from the gravitational tugs of the other moons, it has never been heated much by tidal forces, the stretching and squeezing caused by gravity. This has major effects on what's inside the moon and how it has changed over time. Also, because it's distant from Jupiter, the surface of Kalisto gets hit by far fewer charged particles trapped in Jupiter's magnetic field, about 300 times fewer than Europa, one of the inner moons. This means the radiation hitting Kalisto's surface is much lower compared to the other Galilean moons. The radiation dose on Kalisto is roughly 0.01 rem per day, which is about 10 times higher than the natural background radiation on Earth, but still less than what astronauts get in low Earth orbit or on the surface of Mars. Kalisto has an average density of about 1.83 grams per cubic centimetre. This tells us that Kalisto is made up of roughly equal amounts of rock and water ice, along with some other frozen substances like ammonia. Around 49 to 55% of Kalisto's total mass is made up of these ices. While scientists aren't exactly sure what kinds of rock are inside Kalisto, they think it's similar to a type of meteorite called LLL ordinary chondrites. These meteorites have less iron overall, less metallic iron, and more iron oxide compared to other types like H chondrites. On Kalisto, the weight ratio between iron and silicon ranges from about 0.9 to 1.3, whereas in the Sun, that ratio is roughly 1:8. When we look at Kalisto's surface, it reflects only about 20% of the sunlight that hits it. Its surface makeup is believed to be quite similar to what's inside the Moon. Using near-infrared light studies, scientists have found clear signs of water ice at several specific wavelengths, around 1.04, 1.25, 1.5, 2.0, and 3.0 micrometers. Water ice is everywhere on the surface, making up about 25 to 50% of the material there. But Kalisto's surface isn't just ice. Data from the Galileo spacecraft and telescopes on Earth show that alongside water ice, the surface contains various other materials. These include minerals with magnesium and iron bonded to water, carbon dioxide, sulfur dioxide, and maybe even ammonia, and some organic compounds. When scientists look closely, they see that Kalisto's surface is very mixed up on a small scale. There are tiny bright patches of pure water ice scattered among areas where rock and ice are mixed, and large dark regions made mostly of materials without ice. Interestingly, Kalisto's surface isn't the same all around. The side of the Moon that faces forward in its orbit, called the leading hemisphere, is darker than the side that faces backward, which is called the trailing hemisphere. This is different from Jupiter's other big moons, where usually the leading side is brighter. The trailing side of Kalisto seems to have more carbon dioxide, while the leading side has more sulfur dioxide. Fresh impact craters like Lofn also show higher amounts of carbon dioxide. Overall, the dark areas on Kalisto's surface might be similar in composition to certain types of asteroids called D-type asteroids, which are covered with carbon-rich material. Underneath the surface, Kalisto's crust is cold, hard, and icy, and it's thought to be between 80 and 150 kilometers thick. Scientists believe there may be a salty ocean beneath this crust that's around 150 to 200 kilometers deep. This idea comes from studies of the magnetic fields around Jupiter and its moons. Kalisto reacts to Jupiter's changing magnetic field as if it were a perfect conductor, a solid sphere that the magnetic field cannot penetrate. This suggests there is a layer of highly conductive fluid inside Kalisto that's at least 10 kilometers thick. This fluid layer is probably a salty ocean, and its existence becomes more likely if the water contains a small amount of ammonia or other substances that act like antifreeze, making up as much as 5% of the ocean by weight. In this case, the icy and watery layers together could be as thick as 250 to 300 kilometers. If there isn't such an ocean, the icy crust might be even thicker, up to about 300 kilometers. Beneath the icy crust and this possible ocean, Kalisto's inside doesn't seem to be completely uniform or completely mixed. Data from the Galileo spacecraft, especially measurements of something called the moment of inertia, suggest that if Kalisto's interior is shaped by gravity in a balanced way, called hydrostatic equilibrium, it is made of compressed rocks and ices. The amount of rock increases as you go deeper because some of the heavier materials have settled downward. This means Kalisto might only be partly separated into layers. The density and moment of inertia measurements also suggest there could be a small core made of silicate rock in the center. This core would be no larger than 600 kilometers in radius, with a density between 3.1 and 3.6 grams per cubic centimeter. This partly mixed interior is very different from Ganymede, another of Jupiter's moons, which seems to be fully layered inside. However, in 2011, scientists looked at the Galileo data again and suggested that Kalisto might not be in perfect hydrostatic equilibrium after all. If that is true, the gravity data might better fit a model where Kalisto is more fully layered inside, with a hydrated silicate core. The surface of Kalisto is extremely old and heavily covered in impact craters, more than almost any other place in the solar system. There are so many craters that the surface is close to being saturated, meaning that whenever a new crater forms, it often erases an older one. The overall geology is quite simple. Kalisto does not have tall mountains, volcanoes, or other features formed by internal processes. Instead, its surface is dominated by impact craters, multi-ring structures formed by huge impacts, and the cracks, cliffs, and deposits connected to them. Scientists divide Kalisto's surface into several types of terrain: cratered plains, light plains, bright and dark smooth plains, and special areas connected to big multi-ring formations and impact craters. The cratered plains cover most of the surface and represent the oldest crust made of a mix of ice and rock. The light plains include bright impact craters like Burr and Lofn, old large crater remnants called palimpsests, centers of multi-ring structures, and small patches scattered in the cratered plains. These light plains are thought to be icy deposits left by impacts. Bright, smooth plains are rare and found in certain ridge and valley regions of the Valhalla and Asgard formations, as well as some isolated spots. Scientists once thought these bright plains were caused by internal activity, but detailed images from Galileo showed that they are linked to heavily cracked, bumpy terrain with no signs of recent resurfacing. Galileo also found small, dark, smooth areas, covering less than 10,000 square kilometers, that seem to flow into surrounding terrain. These could be deposits from cryovolcanism, meaning icy volcanoes. Both light plains and smooth plains are younger and have fewer craters than the older cratered plains. Impact craters on Kalisto range widely in size. They can be as small as 1/10 of a kilometer, about 100 meters, up to more than 100 kilometers wide, not counting the massive multi-ring basins. Small craters under 5 kilometers in diameter tend to be simple bowl shapes or have flat floors. Medium-sized craters between 5 and 40 kilometers usually have a peak in the center. Larger craters, from 25 to 100 kilometers wide, often have a pit in the middle instead of a peak, like the Tinder crater. The very largest craters over 60 kilometers can have central domes, which form from the ground rising up after an impact, as seen in the Doe and Haar craters. A few very large bright craters, more than 100 kilometers across, have unusual shallow dome shapes, which might be a step between normal craters and multi-ring structures, like the Loffen crater. In general, Kalisto's craters are shallower than those found on Earth's moon. The largest impact features on Kalisto are the multi-ring basins, huge circular formations with many concentric rings. The biggest of these is called Valhalla. It has a bright center about 600 kilometers wide, with rings that stretch out as far as 1,800 kilometers from the center. The second largest basin is Asgard, which is roughly 1,600 kilometers across. Scientists believe these multi-ring structures formed after a giant impact fractured the icy crust in concentric circles, possibly over a soft or liquid layer like an ocean. Long chains of impact craters, called cateni, for example, Gomul Catena, are also found on Kalisto. These crater chains probably formed when objects were torn apart by Jupiter's gravity, just before hitting Kalisto, or when impacts happened at a very shallow angle. A famous example of such a breakup was the comet Shoemaker-Levy 9, which broke into pieces before hitting Jupiter. As mentioned earlier, some tiny patches of pure water ice on Kalisto's surface shine brightly, reflecting up to 80% of the sunlight. These bright patches mostly appear on higher ground, like crater rims, cliffs, ridges, and knobs. They are probably thin layers of frost made of water ice. Darker material, which usually covers lowlands around the bright features, looks smooth and forms patches up to 5 kilometers wide inside craters and in the areas between craters. When viewed very closely, Kalisto's surface appears more worn down than the surfaces of other icy moons around Jupiter. There are fewer small craters less than 1 kilometer across compared to places like Ganymede's dark plains. Instead of tiny craters, the surface mostly has small knobs and pits. Scientists think these knobs are leftover bits of crater rims that have worn away over time through a process that might be caused by ice slowly turning into gas, called sublimation. This sublimation can happen because temperatures near the point on Kalisto directly facing the Sun can reach up to 165 kelvins, or about minus 108 degrees Celsius. As ice slowly evaporates, the rocky bits left behind break down and cause small landslides called debris avalanches, which fall from the slopes of crater walls. These avalanches often collect near and inside craters, forming what are called debris aprons. Sometimes crater walls have narrow winding valleys called gullies, similar to those seen on Mars. In this picture, the dark material in low areas is thought to be a layer of mostly non-ice debris that came from the worn-down crater rims and now covers mostly icy bedrock underneath. Scientists can estimate the relative ages of different surface areas on Kalisto by counting how many impact craters they contain. The more craters, the older the surface. Although scientists haven't done exact dating, they believe that the cratered plains are about 4.5 billion years old, making them nearly as old as the solar system itself. The ages of the multi-ring basins and impact craters vary depending on different studies, but estimates range from about 1 billion to 4 billion years old. Kalisto has a very thin atmosphere made mostly of carbon dioxide and probably oxygen too. The Galileo spacecraft detected this atmosphere by observing a particular feature near a wavelength of 4.2 micrometers. The atmospheric pressure on the surface is extremely low, about 7.5 picobars, that is 0.75 micropascals, and the density of particles is around 4 times 10 to the 8th power per cubic centimeter. Such a thin atmosphere would normally escape into space in only about 4 years, so it must be constantly replenished. Scientists think this happens by slow sublimation of carbon dioxide ice from Kalisto's crust, which fits with the idea that ice sublimation causes the surface features. Kalisto's ionosphere, an electrically charged layer of the atmosphere, was first discovered during Galileo's flybys. It has a high density of electrons, from about 7 times 10 to the 4th power to 17 times 10 to the 4th power per cubic centimeter, which cannot be explained by sunlight breaking apart carbon dioxide alone. Because of this, scientists suspect that molecular oxygen, in amounts 10 to 100 times greater than carbon dioxide, actually dominates the atmosphere. However, oxygen has not yet been directly detected. Observations by the Hubble Space Telescope set limits on how much oxygen could be present based on the lack of detection, which still fits with the ionosphere measurements. At the same time, Hubble was able to detect frozen oxygen trapped on Kalisto's surface. Scientists have also detected atomic hydrogen in Kalisto's atmosphere by studying Hubble data taken in December of 2001. These studies showed a faint glow of scattered sunlight from hydrogen atoms, forming a kind of hydrogen corona around Kalisto. Interestingly, this glow is about twice as bright when looking at the leading side of the Moon compared to the trailing side. This difference might be because there is more hydrogen on the leading side, but it could also be due to interference from Earth's own hydrogen cloud, which blocks the signal more when observing the trailing side. Looking inside Kalisto, scientists believe it is only partly layered or differentiated. This means the Moon has not been heated enough to melt its ice and separate its materials fully. Measurements of Kalisto's rotation and shape support this idea. The most likely way Kalisto formed is by slowly gathering together material from a thin disk of gas and dust that surrounded young Jupiter, called the Jovian subnebula. This slow formation, taking anywhere from 100,000 to 10 million years, allowed Kalisto to cool enough during its growth so it didn't melt much from the heat, caused by impacts, radioactive decay, or shrinking. After Kalisto was formed, its internal changes depended on a balance between heat generated by radioactive elements inside, heat lost through its surface, and a very slow process called subsolidus convection. This convection is when ice inside the Moon slowly moves in solid form, just below its melting point. Ice's thickness and stiffness cause the surface to stay cold and rigid, forming a lithosphere about 100 kilometers thick, while ice beneath this layer slowly circulates like a very slow-moving liquid. This slow ice movement, about 1 centimeter per year, actually helps cool Kalisto over millions or billions of years. The convection may happen in layers because under extreme pressure inside Kalisto, water ice changes into different forms, from normal ice near the surface to exotic types deep inside. Because of this slow convection, Kalisto never melted enough to form a big, distinct rocky core and an icy shell like some other moons. Instead, small amounts of rock and ice have slowly separated over billions of years, and this process may still be going on now. Scientists also think there might be a hidden ocean of liquid water inside Kalisto. This is because the temperature and pressure in a layer about 100 to 200 kilometers deep are very close to the melting point of ice, which behaves strangely at high pressures. At around 2070 bars and very cold temperatures near 251 Kelvin, ice can melt. Even tiny amounts of ammonia in this layer, only 1 to 2% by weight, would lower the melting point enough to keep this ocean liquid. Compared to its neighbour Ganymede, Kalisto seems to have had a simpler and calmer geological past. Its surface mostly shows signs of impacts from asteroids and comets, but little evidence of tectonic or volcanic activity. Unlike Ganymede's grooved and complex terrain, Kalisto's landscape looks more plain. Scientists believe the differences come from how the moons formed, how much tidal heating they experienced, and the number and intensity of impacts they each had during an event called the Late Heavy Bombardment billions of years ago. Because Kalisto's history is simpler, it gives scientists a useful example to compare with more geologically active worlds. There is also speculation that life might exist in Kalisto's underground ocean. Like Europa and Ganymede, as well as moons around Saturn and Neptune, Kalisto's ocean could be salty, which helps support life in extreme conditions here on Earth. Tiny, hardy microbes called halophiles might be able to survive in this environment. Still, conditions for life on Kalisto seem less favourable than on Europa, because Kalisto's ocean doesn't have as much heat coming from the moon's interior and doesn't mix as much with rocky material. Europa's ocean is warmed both by radioactive decay and by tidal forces because it is much closer to Jupiter, so scientists think Europa has the best chance among Jupiter's moons to host microbial life. Ideas about Kalisto's lighter, icy composition go back nearly 100 years. In 1923, Harold Jeffreys suggested it might be lighter than pure rock, and in 1931, Gustav Tammann agreed. In 1951, Jeffreys also proposed it contained water ice. Our knowledge about Kalisto improved slowly. The Pioneer spacecraft missions in the early 1970s gave limited new information compared to Earth-based observations. The real breakthroughs came with the Voyager 1 and Voyager 2 flybys in 1979, which photographed more than half of Kalisto's surface in detail, measuring its temperature, mass, and shape precisely. Then, from 1994 to 2003, the Galileo spacecraft made 8 close passes near Kalisto, getting as close as 138 kilometers to the surface and completing a detailed global map. The Galileo mission took pictures with incredible detail, showing areas as small as 15 meters across. In 2000, the Cassini spacecraft, while traveling to Saturn, also gathered detailed infrared data of Kalisto. Later, in February and March of 2007, the New Horizons probe, on its way to Pluto, snapped new images and took spectral readings of Kalisto. Looking to the future, 3 spacecraft are planned to visit Kalisto soon. The European Space Agency's Jupiter Icy Moons Explorer, or JUICE, launched in mid-April 2023. It will perform 21 close flybys of Kalisto between 2031 and 2034. NASA's Europa Clipper, launched in mid-October 2024, will make 9 close flybys of Kalisto starting in 2030. China's space agency plans to send its Tianwen-4 mission to Jupiter around 2030 and hopes to put it into orbit around Kalisto. Before these missions, there was a joint NASA and ESA proposal called the Europa Jupiter System Mission, announced as a priority in early 2009. It planned to send multiple spacecraft to study Jupiter's moons, but faced some funding challenges. NASA also explored the idea of humans visiting Kalisto. In 2003, NASA studied the possibility of building a base on Kalisto that could produce rocket fuel for deeper space missions. This idea was appealing because Kalisto has low radiation levels, thanks to its distance from Jupiter and a stable surface with little geological activity. Such a base could help explore Europa remotely, or serve as a way station for spacecraft travelling further into the outer solar system. NASA even suggested in December 2003 that a human mission to Kalisto might be possible sometime in the 1940s. Ganymede is one of the moons that orbits the giant planet Jupiter, and it holds a very special place in our solar system. It is not only the largest moon of Jupiter, but also the biggest and heaviest moon in the entire solar system. In fact, Ganymede is even bigger than the planet Mercury. However, because Ganymede is made of lighter materials, it has a bit less surface gravity than Mercury, as well as less gravity than some of Jupiter's other moons like Io, and even less than our own moon here on Earth. Ganymede takes about 7 Earth days to complete one full orbit around Jupiter. It also has a fascinating orbital dance with 2 of its neighbouring moons, Europa and Io. This is called a 1:2:4 orbital resonance, meaning that for every orbit Ganymede makes, Europa goes around twice and Io goes around 4 times. This kind of orbital relationship helps to keep their motion stable and influences their internal heating and geological activity. The inside of Ganymede is made up roughly of equal parts rocky material and water ice. Unlike a simple lump of rock and ice, Ganymede is a fully differentiated world. This means its materials are layered inside, much like Earth, with a dense iron-rich core at the centre. This core is liquid and metallic, and it gives Ganymede a very low moment of inertia, a measure of how mass is distributed inside the Moon. This low value tells us that most of Ganymede's heavy stuff is packed near the centre. Scientists believe beneath the surface lies a deep ocean of liquid water, which may hold more water than all the oceans on Earth combined. Ganymede is also unique because it has its own magnetic field. This magnetic field likely comes from movement or convection within its liquid iron core. On top of that, Jupiter's own powerful magnetic field also affects Ganymede's, adding complexity to the magnetic environment around the Moon. Surrounding Ganymede is a very thin atmosphere, mostly made up of oxygen. This atmosphere contains atomic oxygen, O, molecular oxygen, O2, and possibly ozone, 3. There is also a tiny amount of atomic hydrogen floating around. Scientists are still not sure if this atmosphere has an ionosphere, a layer of charged particles like Earth's ionosphere, but it is something they continue to study. Looking at Ganymede's surface, we find 2 main types of terrain. About 2/3 of the surface is covered by lighter coloured regions, filled with many grooves and ridges. These features formed around 4 billion years ago and might be the result of tectonic activity, movements in the icy crust caused by the gravitational pull and tidal heating from Jupiter. The other one-third of the surface is made of darker, heavily cratered regions, which are about the same age as the light terrain, around 4 billion years old. Ganymede was discovered in the year 1610 by two famous astronomers, Simon Marius and Galileo Galilei. It was the third of the 4 big moons around Jupiter that Galileo spotted, the first time humans discovered objects orbiting a planet other than the Sun. The moon's name comes from Simon Marius, who named it after the mythological figure Ganymede, a handsome prince from Troy who was carried off by Zeus, the Greek god equivalent to Jupiter, to serve as cupbearer to the gods. Since then, many spacecraft have visited Ganymede to learn more about it. The Pioneer 10 spacecraft was the first to explore Jupiter and its moons. Later, the Voyager 1 and Voyager 2 probes helped scientists measure Ganymede's size more accurately. The Galileo spacecraft, which orbited Jupiter in the 1990s and early 2000s, discovered the hidden ocean beneath Ganymede's surface and confirmed its magnetic field. Looking ahead, the European Space Agency launched the Jupiter Icy Moons Explorer known as JUICE in the year 2023. JUICE will fly by all 3 of Jupiter's large icy moons, including Ganymede, before settling into orbit around Ganymede itself to study it in detail. Ganymede has a diameter of about 5,270 kilometers, which is roughly 3,270 miles. This makes it the largest moon in the solar system. It weighs around 148 quintillion tons, 1.48 times 10 to the power of 23 kilograms. It is a little heavier than Saturn's largest moon Titan and more than twice as heavy as Earth's moon. Even though it is bigger than Mercury, it only has about 45% of Mercury's mass. The average density of Ganymede is about 1.936 grams per cubic centimetre. This tells us that Ganymede is made up of roughly equal amounts of rock and water ice, with the ice being mostly frozen but some hidden in liquid form beneath the surface. The amount of ice on Ganymede is estimated to be between 46 and 50% of its total mass, which is slightly less ice than what is found on Kalisto, another large icy moon. Scientists think some of this ice might include other frozen substances, like ammonia. The exact makeup of Ganymede's rocky part isn't fully known, but it probably resembles a type of ordinary meteorites called L or LL chondrites. These have less metallic iron and more iron oxide compared to some other meteorites. When comparing the amounts of iron to silicon, Ganymede has a ratio between about 1.05 and 1.27, which is lower than the Sun's iron to silicon ratio of around 1.8. The surface of Ganymede shines with an albedo or reflectivity of about 43%. This means it reflects nearly half of the sunlight that hits it. Water ice covers much of the surface, making up between 50 and 90% of the surface material, much more ice than is found inside the moon overall. By using special instruments that detect infrared light, scientists have found strong signs of water ice, showing specific patterns at several wavelengths. The grooved terrain is especially bright and icy compared to the darker regions. Further studies, including data from the Galileo spacecraft and Earth-based telescopes, have revealed that Ganymede's surface also contains other chemicals besides water ice. These include carbon dioxide, sulfur dioxide, and possibly cyanogen, hydrogen sulfate, and some organic compounds, complex molecules containing carbon. The presence of salts like magnesium sulfate and sodium sulfate was also detected, and these may have come up from the hidden ocean inside Ganymede. Interestingly, the surface brightness is uneven across the moon. The leading hemisphere, the side that faces forward in Ganymede's orbit, is brighter than the trailing hemisphere. This pattern is similar to what we see on Europa, but it is the opposite of what happens on Kalisto. The darker trailing hemisphere has more sulfur dioxide, while carbon dioxide is spread more evenly, but tends to be scarce near the poles. Impact craters on Ganymede generally don't show signs of extra carbon dioxide, which sets it apart from Kalisto. Scientists think that in the past, carbon dioxide on Ganymede was depleted, possibly lost to space or buried. The two types of surface terrain, dark and light, tell different stories. The dark areas, making up about 1/3 of the surface, are old and covered in many craters. These craters were caused by countless impacts over billions of years and might contain clays and organic materials, which hint at the original building blocks that formed Jupiter's moons. The lighter grooved terrain, which covers the rest of the surface, has fewer craters and shows signs of tectonic activity, movements and stretching of the icy crust that reshaped much of the landscape. How exactly this grooved terrain formed is still a puzzle for scientists. The most popular idea is that tectonic forces caused the cracking and ridges, mainly due to stresses from tidal heating, the squeezing and stretching of Ganymede by Jupiter's gravity over time. Some thought that icy volcanoes, cryovolcanism, might have played a part, but that seems to have been minor if it happened at all. The tidal forces may have heated Ganymede's interior and caused its icy shell to crack and shift, wiping away the older, dark terrain on about 70% of the surface. This process could be linked to Ganymede's early history, when its core formed and its orbit passed through unstable phases that increased tidal heating. Scientists also think that as Ganymede's interior heated up, hot plumes of water might have risen through the icy shell, further shaping the surface by pushing and pulling on the crust. Today, the main heat source inside Ganymede is radioactive decay, slowly warming the interior. However, models show that if Ganymede's orbit were more elliptical in the past, tidal heating could have been an even stronger source of heat. Impact craters appear on both the dark and light terrains, but they are especially common in the dark regions, which seem to be saturated with craters. The lighter grooved regions have far fewer craters, indicating a younger surface. The number and appearance of craters suggest that the dark terrain is about 4 billion years old, similar in age to the lunar highlands on the Moon. The grooved terrain is younger, but scientists are not sure exactly how much younger. Ganymede likely experienced a period of heavy cratering between 3.5 to 4 billion years ago, like the Moon. Since then, fewer impacts have occurred. Some craters cross-cut the grooves, showing that the grooves themselves are also ancient. There are even some relatively young craters with bright rays of ejected material. Compared to craters on the Moon or Mercury, Ganymede's craters tend to be flatter. This is probably because its icy crust is softer and can slowly flow, smoothing out the crater shapes over time. Some ancient craters have almost completely disappeared, leaving only faint ghost outlines known as palimpsests. One of the most noticeable features on Ganymede is a large dark area called Galileo Regio. This region is covered with concentric grooves or furrows, which were likely formed during an ancient period of geological activity. Ganymede also has polar caps made mostly of water frost, which stretch down to about 40 degrees latitude from the poles. These icy caps were first spotted by the Voyager spacecraft. Scientists believe that the frost formed either because water ice moved to colder, higher latitudes, or because charged particles from Jupiter's magnetic field bombarded the poles, causing ice to sputter and migrate. Data from the Galileo mission support the idea that charged particle bombardment plays a major role in shaping the polar frost. To map locations on Ganymede, scientists use a crater named Anat as a reference point. By definition, Anat is located at 128 degrees longitude. The 0-degree longitude line points directly at Jupiter, and longitudes increase westward unless otherwise specified. Inside, Ganymede is fully layered with a structure made up of an iron sulfide and iron core at the centre, surrounded by a rocky mantle and covered by layers of water ice and liquid water. The exact thickness of each layer depends on the rock composition and the amount of sulfur in the core. Thanks to this layered structure and its significant water content, Ganymede has the lowest moment of inertia factor, around 0.31, among all solid bodies in the solar system. Back in the 1970s, NASA scientists first suggested that Ganymede might have a thick ocean trapped between layers of ice, a surface ice shell, a hidden liquid water ocean beneath, and then another layer of ice above the rocky interior. In the 1990s, NASA's Galileo spacecraft flew close to Ganymede and found strong evidence for this subsurface ocean. Later studies, including a detailed analysis published in 2014, indicated that Ganymede could have multiple layers of oceans separated by different types of ice, with the lowest liquid layer touching the rocky mantle. This is important because where water meets rock, conditions might be right for life to form. The ocean beneath Ganymede's ice could be as deep as 800 kilometers, and due to pressure and heat, temperatures at the ocean floor might be up to 40 Kelvin warmer than at the ice water boundary above. In March of 2015, Scientists used the Hubble Space Telescope to watch the movement of auroras, bright glowing lights in Ganymede's atmosphere caused by charged particles, and these observations confirm the presence of the underground ocean. A large, salty ocean influences the magnetic field, and in turn the auroras, proving that the ocean is there. This ocean may be the largest one in the entire solar system. More recently, NASA's Juno spacecraft detected various salts and chemicals on Ganymede's surface, such as hydrated sodium chloride, common salt, ammonium chloride, sodium bicarbonate, and possibly some organic molecules. These were likely brought to the surface from the ocean during past geological activity. These compounds are most common near Ganymede's lower latitudes, protected by the Moon's own magnetic shield. These discoveries have increased interest in whether Ganymede's ocean could potentially support life. The liquid iron-nickel core inside Ganymede is also the natural source of its magnetic field, which was first detected by the Galileo spacecraft. Scientists believe that convection, movement of the liquid metal caused by heat, in the electrically conductive core generates this magnetic field, much like a dynamo. The core's density is about 5.5 to 6 grams per cubic centimetre, while the rocky mantle above it has a density around 3.4 to 3.6 grams per cubic centimetre. The core's radius may be up to 500 kilometres, and the temperature inside could be between 1500 and 1700 Kelvin. The pressure inside reaches nearly 10 gigapascals, which is about 99,000 times the air pressure at Earth's surface. Europa is one of the many moons that circle the giant planet Jupiter. It is special because it is one of the 4 big moons discovered by the famous astronomer Galileo Galilei back in the early 1700s. These moons are called the Galilean moons, and Europa is the smallest and lightest of them all. It is even a little smaller and lighter than Earth's own moon. You can actually see Europa from Earth with just a good pair of binoculars, which is pretty amazing considering how far away it is. Europa is covered mostly with ice, making it one of the icy moons of Jupiter. It orbits closest to Jupiter among the 3 icy Galilean moons. Because of its close orbit, Europa's surface is relatively young and smooth compared to many other moons. This is because the strong gravitational pull from Jupiter causes the moon to flex and stretch as it moves around, creating heat inside Europa, a process called tidal heating, which helps keep its surface fresh and active. Inside, Europa probably has a core made of iron and nickel, similar to Earth's core, surrounded mostly by rocky material. On top of that lies a thick shell of water ice. This moon has a very thin atmosphere made mostly of oxygen, but it is far too thin to breathe. When we look at Europa's surface through telescopes and from spacecraft, we see a smooth, bright landscape, mostly white and beige in colour, with many cracks and streaks running across it. Interestingly, there are hardly any large impact craters, meaning its surface has been renewed often by geological activity. Since the 1970s, Europa has been studied by several space missions that have flown close by. Most recently, in September of 2022, NASA's Juno spacecraft zoomed in within about 320 kilometers of Europa, giving us some of the best close-up views of this mysterious moon. One of the most fascinating things about Europa is that it has the smoothest surface of any solid object we know in the whole solar system. Scientists believe this smoothness comes from a hidden ocean of liquid water beneath the icy crust. This underground ocean might even be a place where life could exist far away from Earth. The heat from the constant squeezing and stretching caused by Jupiter's gravity keeps this ocean liquid, and the icy shell above moves slowly, somewhat like the shifting plates of Earth's crust. This movement could allow chemicals from the surface ice to mix with the ocean water below, which might be important for life. Some salty sea minerals seem to coat parts of Europa's surface, hinting that the ocean below interacts with the rocky sea floor. The Hubble Space Telescope has spotted plumes of water vapour, like geysers, shooting out from Europa's surface, similar to those found on Saturn's moon Enceladus. These icy jets are likely caused by cryogeysers, which are like cold volcanoes erupting water instead of lava. In May of 2018, scientists found more evidence supporting these water plumes based on data from the Galileo space probe that orbited Jupiter during the 1990s and early 2000s. These plumes are exciting because they might let future missions study Europa's ocean without needing to land and drill through thick ice. In March of 2024, researchers also discovered that Europa's surface might have much less oxygen than they once thought, which changes how we think about its atmosphere and potential habitability. Europa was discovered by two astronomers almost at the same time, Simon Marius and Galileo Galilei. The name Europa comes from a figure in ancient Greek mythology, a Phoenician princess who was loved by Zeus, the Greek god who is like Jupiter in Roman stories. The Galileo mission, which launched in 1989, gave us most of what we currently know about Europa. Although no spacecraft has landed on Europa yet, there are several missions planned. For example, the European Space Agency's Jupiter Icy Moons Explorer, called JUICE, launched on the 14th of April 2023. JUICE will fly by Europa twice during its mission, which focuses mainly on the bigger moon Ganymede. NASA's Europa Clipper mission launched later, on the 14th of October 2024, and will study Europa in even more detail. Europa is just a little smaller than Earth's moon, with a diameter of just over 3,100 kilometers, about 1,900 miles. This makes it the 6th largest moon in the solar system and the 15th largest object overall. Compared to the other Galilean moons, Europa has the lowest mass, and its makeup is similar to rocky planets like Earth, mostly silicate rock. Scientists estimate that Europa's outer shell of water is roughly 100 kilometers thick. Part of this is frozen solid as the icy crust we see, and underneath lies a deep, salty ocean of liquid water. Data from the Galileo spacecraft also showed that Europa has a magnetic field created by its interaction with Jupiter's massive magnetic field. This suggests the salty ocean beneath the surface conducts electricity. Interestingly, some parts of Europa's ice shell appear to have rotated almost 80 degrees, nearly flipping over in a process called true polar wander. This movement hints that the icy shell isn't firmly stuck to the rocky interior beneath. Europa's surface temperatures are extremely cold, averaging around minus 160 degrees Celsius at the equator, and dropping even lower to about minus 220 degrees Celsius, minus 370 degrees Fahrenheit, at the poles. This means the ice is as hard as granite, making it a very solid crust. Scientists first guessed there might be a hidden ocean beneath Europa's ice by studying how tidal forces from Jupiter stretch and squeeze the moon as it orbits. Photos from the Voyager and Galileo spacecraft showed signs of a young and active surface, including chaos terrain, areas of broken, jumbled ice that some believe might have formed where the ocean melted through the crust. However, this is still debated. Most scientists think Europa has a thick ice shell, about 10 to 30 kilometers, 6 to 20 miles, thick, which keeps the ocean sealed beneath. Inside this shell, there might be a warm ice layer that bends and flows slowly. This suggests the liquid ocean under the ice could be around 100 kilometers deep, meaning Europa's ocean might hold 2 to 3 times as much water as all of Earth's oceans combined. Some researchers have proposed a thin ice model, where the ice shell is just a few kilometers thick, allowing the ocean to sometimes touch the surface through cracks or ridges. But this idea is less popular among experts because it only accounts for the very top layer of ice, which behaves like a flexible skin under Jupiter's strong tides. Europa's magnetic field, although weak, is about 1/6 as strong as that of Ganymede and 6 times stronger than Kalisto's, other Galilean moons. This supports the idea of a salty liquid ocean underneath that conducts electricity. The reddish-brown stains seen on Europa's surface have puzzled scientists for years. They think these colours come from salt minerals like magnesium sulfate left behind when ocean water evaporates through cracks in the ice. Another possibility is sulfuric acid compounds from Jupiter's radiation affecting the surface. Some think organic chemicals called tholins might also be responsible. These complex molecules form when sunlight or radiation breaks down simpler compounds and may be important for the chemistry of life. Further observations from the Hubble Space Telescope and the James Webb Space Telescope reveal variations in ice types and surface chemistry across Europa's northern and southern hemispheres. These studies suggest Europa's surface ice is constantly being reshaped by radiation and thermal processes. In 2012, the Hubble Space Telescope spotted a giant plume of water vapor erupting from near Europa's south pole. This plume might have reached heights of about 200 kilometers, which is more than 20 times taller than Mount Everest. However, newer research suggests these plumes might usually be much smaller and only appear occasionally, especially when Europa is farthest from Jupiter in its orbit. In November 2020, scientists proposed a new idea that these water plumes could come from pockets of salty water trapped within the icy crust itself, which freeze and build pressure until they burst through the surface. This cryovolcanic activity would be different from eruptions coming straight from the ocean below. If true, it could mean that some plumes might be less friendly to life, lacking the energy sources found near ocean vents. Europa's tidal forces from Jupiter are incredibly strong, about 1,000 times stronger than the moon's pull on Earth. So far, only one other moon, Enceladus around Saturn, has been seen to have similar water vapour plumes. Europa's estimated plume eruption rate is about 7,000 kilograms of water per second, much higher than Enceladus's 200 kilograms per second. If these plumes are confirmed and sampled by spacecraft, scientists could learn a lot about Europa's ocean and whether it might support life, without having to land and drill through kilometers of ice. This makes Europa one of the most exciting places to explore in our solar system. Europa is the smoothest object we know in the entire solar system. It does not have big features like mountains or many craters. The noticeable lines and patterns you see crossing Europa are mostly caused by changes in how much light the surface reflects, showing areas that are lower or flatter. There are very few craters on Europa because its surface is always moving and changing, making it quite young in age. These craters contain salty minerals that come from underneath the surface, but hardly any sulfuric acid, which tells us that these craters were formed quite recently. Europa's icy surface reflects a lot of sunlight, about 64% of the light that hits it, which is one of the highest reflectivity levels of any moon. This also shows that Europa's surface is young and active. Scientists estimate that the surface is between 20 million and 180 million years old based on how often comets hit it. Some scientists think that near Europa's equator, there might be tall, thin, icy spikes called penitentes, which could be as tall as 15 meters. These might form because the sun shines directly overhead, causing the ice to slowly turn from solid to gas and create cracks that grow upward. We don't have clear pictures to confirm this yet, but radar and heat measurements support this idea. The radiation on Europa's surface is very strong, about 5.4 sieverts every day. This amount of radiation would make a human very sick, or even cause death if exposed for just one Earth day. But one day on Europa lasts about 3.5 times longer than an Earth day. One of Europa's most eye-catching surface features is a set of dark streaks called lineae, which cross the whole moon like lines on a globe. If you look closely, the edges of these cracks have moved sideways relative to each other. Some of these bands are wider than 20 kilometers and have darker edges with regular stripes and a lighter band in the middle. The most likely explanation is that these lineae were created by eruptions of warm ice as Europa's crust slowly spreads apart, exposing warmer ice underneath. This process is similar to what happens at Earth's ocean ridges where the seafloor spreads. These cracks are thought to be caused mainly by Jupiter's strong gravitational pull, flexing Europa's surface. Since Europa always shows the same face to Jupiter because it is tidally locked, the cracks should form in a predictable pattern, but only the newest cracks fit this pattern. Older cracks seem to be oriented in different directions. This might be because Europa's icy outer shell rotates slightly faster than its deeper interior, thanks to a global ocean under the ice that allows the surface to move separately from the rocky core. Jupiter's gravity also pulls on the ice shell, affecting how it moves. Comparing photos from the Voyager and Galileo spacecraft helps us guess how fast this slippage happens. It seems that Europa's outer shell takes at least 12,000 years to make one full rotation compared to its inner parts. Studies of these spacecraft images show signs of something like plate tectonics on Europa, similar to Earth's. Just like ocean ridges on Earth where new crust forms, there are areas on Europa where the icy crust seems to spread apart, and in other places the crust appears to sink back down, recycling itself. This suggests Europa's icy surface might be slowly moving like tectonic plates. However, the forces causing this movement on Europa are likely very different and stronger than those on Earth, so the process isn't exactly the same. Europa also has round or oval spots called lenticulae, which means freckles in Latin. Some are dome-shaped, some are pits, and some are smooth dark spots, while others look rough or jumbled. The dome tops seem to be pieces of the older surface pushed upward from below, One idea is that these lenticular form when warmer ice rises through the colder outer ice, like magma chambers rising in Earth's crust. The smooth dark spots could be areas where meltwater escapes to the surface when the warm ice breaks through. The rough, jumbled lenticular, sometimes called chaos regions like Connemara Chaos, might be made of many small broken pieces of ice crust surrounded by dark, uneven material, looking like icebergs in a frozen sea. Another idea suggests that these lenticulae are actually small patches of chaos, and that the pits, spots and domes people see might just be mistakes from looking at blurry early images from the Galileo spacecraft. This would mean the ice is too thin to support warm ice rising up as the first idea suggested,